Good morning, everybody. I'm not going to talk about Professor Dibyendu Nandi's career, but I'm only going to highlight the achievements for which the Young Career Award is being awarded. So let me read the citation. Dibyendu has made fundamental contributions to understanding the origin and fluctuations in the sun's activity, including uncovering the physics of solar cycle predictability and establishing the short one-cycle memory of the sunspot cycle. He has also made significant contributions to other areas, such as the development of data-driven global coronal field evolution models, constraining the kinematics of coronal mass ejections, exploring the role of magnetic helicity in coronal heating and solar flaring activity, and establishing how solar internal plasma flow variations introduce asymmetries in the sunspot cycle. In more recent years, he has contributed to the development of computational models to explore star-planet interactions in solar and exoplanetary systems. The Young Career Award for the 5th Asia-Pacific Solar Physics Meeting is conferred on Dibyendu for his contributions to the science of solar physics and solar physics community.
Oh, yeah, okay, all right, sure. Okay, thanks. Wow, okay. All right. So, thank you. Thank you. Okay. Okay, thanks, Siraj. Okay, let me get this out of the way. Sorry? Okay, yeah, sure, whatever. Okay. Okay. All right. Thank you very much. Thank you to the Asia Physics, Solar Physics Society for this honor. I take responsibility for the work I'm going to speak about. I don't take responsibility for the definition of youth in this. I was actually invited to give a talk in this conference before the award was announced. And then when the award was announced, Durgesh called me up and said, hey, you can't possibly give 2 lectures, so you give 1 lecture. I said, no, I can give 2 lectures. Durgesh said, no, 1. Okay, so I have decided to actually give 3 different talks as part of this one, which you will soon find out. Okay, so the focus of my research has been on understanding the variability of the sun and its impact on the inner heliosphere as well as the planets that inhabit the solar system. The studies are important because the solar system not only provides astrophysical laboratory for testing our fundamental physics ideas about magnetodynamics in the universe, but it also allows us to take these ideas and develop models which you can, in principle, use for predictions of the system and check it out through observations which is possible in the solar system, given the large number of satellites and observatories we have looking at the solar system. So this is a perfect place to actually develop fundamental physics models to predictive models and have a sort of a window to the plasma universe. So I generally look at the system in a computer, like a box, and I try to figure this out. We start from the physics, and from there we go into developing data-driven models. And as we develop models, typically a good model is a model that should be able to make predictions for a system, right? So you try to push these models to make predictions, and you do make predictions. And when it works out, you know that you have a good understanding of the underlying physics. And then sometimes you have the oh crap moment, and for that you have this, where you go back and you sort of go through the cycle of including the physics that you thought you missed out, and refining your understanding and the models. So if you look at the inner heliosphere, I can divide this into 3 distinct physical regimes. The first regime is in the interior of the sun, the star. And this regime has high plasma beta, which implies that the magnetic fields are dominated by the plasma flows, and is the plasma flows in the solar interior, which sort of govern the evolution and dynamics of the solar activity. Once this activity is produced, it emerges out of the solar surface as sunspots, and it permeates the corona, which sort of provides the boundary to the inner heliosphere. And the coronal plasma is pretty tenuous. The gas density is very low, so the plasma pressure falls, and then you have a low beta sort of regime in the corona, and the physics is slightly different from the interior. And then if you go beyond, further out into the heliosphere, closer to the planets, then you have this interesting physics of star-planet interactions, where the activity that you generate can, in principle, impact the magnetospheres and atmospheres of planets, and over evolutionary timescales of any solar system or exoplanetary systems can, in principle, play a big role in the evolution of the atmospheres of planets. So what I'll do today is I will give you a glimpse of 3 different problems that I've been involved in the last 10 years or so. The first one is to explore the physics of solar cycle predictability. The second one is to develop data-driven models of coronal field evolution, and to push this to make predictions of the solar coronal field. And the third aspect that I'm going to be talking about today is star-planet interactions. I'll give you a brief introduction to this field at the end, and talk of some of the early results from some work that we've initiated in this area, which has relevance for not only the solar system, but beyond. Okay, so if you look at the sun, and this is the recent image released by Dickist last week. The quiet sun looks mostly like this. In this image, what you see is convective granules, and of course, deeper down, the interaction of convection and large-scale plasma flows are thought to produce the sunspot cycle, which is manifested as sunspots on the solar surface, which can be used both as a pressure to set constraints on the long-term solar activity, and the sunspots also eventually govern most of the dynamic activity that you see from stars like the sun. If you look at the sunspot time series, and this exists for the last 4 centuries, what we know is that there is a sunspot cycle. The periodicity of the cycle is on the average about 11 years, but the amplitude of the cycle is highly variable. And the question is, do you understand the underlying physics of the sunspot cycle good enough to be able to predict the solar activity cycle? So if you go back a decade to the beginning of sunspot cycle 24, let's say about circa 2008, and look at how we did in terms of the sunspot cycle prediction. When you look at the whole time series, you see that other than the Monroe minimum, the typically annually average sunspot number ranges from about 40 to about 180. If you look at the predictions for just one sunspot cycle 24, it spanned the entire range of all sunspot cycles ever observed, and even the 2 Dynamo-based predictions diverged quite a bit, which sort of, makes you think that this business was a bit like this, right? Okay, so let me set the context here. So it's important to appreciate that when you understand, when you believe that you understand the underpinnings of a physical system well enough, then I believe that you can move this understanding to make predictions of the system. And if you look at the sort of an analogous system like the Earth's atmosphere, weather predictions and climate predictions have reached some level of maturity. However, this has not been possible in terms of predicting the sunspot cycle, right? This is what is desirable. Now, what are the outstanding questions that one might ask or pose when you try to address the physics of sunspot cycle predictability? So the first question is it possible to predict the sunspot cycle at all? And if yes, then what is the best proxy or precursor for this prediction? Do we understand why this physics-based predictions for the sunspot cycle 24 diverged so widely? Now, what can we predict in terms of the properties of the sunspot cycle, and how accurately? And how early can you make this prediction? And what is the predicted outlook for the next transport cycle, say solar cycle 25? So if you believe that we have made a progress in terms of addressing the underlying physics, we should be able to make a prediction for transport cycle 25, which you would wait to test with the actual phenomena to see if you got it right or wrong, right? Okay, so this is important to keep in mind, that organized efforts to predict weather or climate on Earth has been made for the last half a century, whereas organized efforts to look at transport cycle predictability has only happened over the last 2 decades, and mostly, in fact, over the last decade. Okay, so let's look at the physics of stars like the sun. So energy is generated in the solar interior, and then it's radiated out to the radiation zone, and the outer convection zone is opaque to radiation, so you have large-scale convection, which transports heat. And because the temperature is so high in the solar interior, matter is ionized. So essentially, you have large currents of plasma, which is a perfect system for producing magnetic fields. And we believe the magnetic fields are produced in the outer convection zone, where you have these large-scale motions. So if you look at the governing equation for such a system, then it's the induction equation, which arises out of the Maxwell's equations and the Ohm's law. So this governs the evolution of a magnetic field B given a plasma velocity V and a turbulent diffusivity eta. If you take the ratio of the first term to the second term on the right-hand side, then you get a dimensionless number known as the magnetic Reynolds number, which is a product of the velocity and length scales of the system divided by the turbulent diffusivity in the system. Now, typically in astrophysical systems, this magnetic Reynolds number is very high, which implies that the first term on the right-hand side, which is the source term, dominates. And interestingly, this can also be reduced to be the ratio of the diffusion time scale to the flow time scale in the system, the Reynolds number. What this implies is that the flow dominates the dynamics, and it can twist, turn, stretch, and induct magnetic fields to produce dynamo action. The other important aspect, which I already noted, is the plasma beta parameter. The ratio of gas pressure to magnetic pressure is pretty high in the solar convection zone, which implies that the gas dynamics, which is the plasma dynamics and flows, govern the overall sort of dynamics in the system there, and can induct magnetic fields, and the energy in the convection and large-scale flows can be drawn in to generate magnetic energy through dynamo action. And typically, the efficiency of the dynamo mechanism is measured in terms of the dynamo number, which depends on a lot of parameters, but principally you can reduce it to the solar differential rotation, and also the helicity content in the system, which depends on the rotation rate and the Coriolis force. So astrophysical systems which are strongly rotating actually have stronger activity, and this is known in observations across stars, right? So what we understand of the solar dynamo mechanism is this, that if you have a pre-existing poloidal field, which is in the r theta plane of the sun, this can be stretched by the differential rotation in the phi direction to produce the toroidal component. And strong toroidal flux tubes are magnetically buoyant, and they can erupt out of the convection zone and reach the surface to form sunspots. And while these flux tubes are moving up to the convection zone, the Coriolis force imparts tilts, giving rise to tilted bipolar active regions. Now, a combination of processes, which could be the mean field alpha effect, which is driven by turbulent helicity, turbulent convection, and also the decay and dispersal of the tilted bipolar active regions on the solar surface, which is known as the Bappo-Clayton mechanism, can recreate the large-scale polar field of the sun through some surface flux transport processes. And then subsequently, again, the poloidal field can create the toroidal field for the next cycle. And so the cycle goes on, right? Except that, the sunspot cycle is not like this. It's not a sinusoid. There are variations in the amplitude. And to appreciate this variability and to be able to predict it, one has to understand where these variations in the amplitude, the modulation of cycle amplitude comes from. Okay, so before that, let us talk a little bit about what is the dominant contributor to the poloidal field, because if you're trying to make a model to make predictions, you should also be able to properly address the dominant mechanism that creates an important component of the solar field. So if you look at this observational plot, which plots the Bappo-Clayton source term versus the sunspot cycle amplitude of the next cycle, you see a reasonably good correlation between the two, which implies that the backpropagation source is the dominant driver of the variability in the sunspot cycle. So this is observational. And then in 2015, Robert Cameron and Manfred Schussler wrote a paper, which is a completely theoretical paper based on an understanding of the applications of electromagnetism to the solar surface and the distribution of flux distribution, claiming that the backpropagation mechanism is the only mechanism required to explain the observed variability of the sun. So both from theoretical viewpoints as well as observational viewpoints, there has been some hints that the dominant contributor to the poloidal field mechanism is in fact the backpropagation mechanism. Okay, so now if you look at the variability, so there are various processes in the convection zone due to the turbulent nature of the convection zone, which can perturb the system and introduce fluctuations. So one of these is the turbulent buffeting of rising flux tubes when they're rising to the base of the convection zone to erupt as sunspots, which gives rise to a dispersion or scatter in the tilt angle around the mean. The mean is the Joy's law. And this dispersion can, in principle, create cycle-to-cycle variability, right? Okay. There are other effects, and those effects are essentially due to the nonlinearities in the system. And there have been various theories postulating about the nonlinearities that can, in principle, introduce long-term cycle modulation. These are the Lorentz feedback, heliocentric quenching, time delays in the system, and more recently, related to the backpropagation mechanism, the feedback of the magnetic fields on the surface flows, the surface meridional circulation, which sort of, it perturbs the system in such a way that it creates inflows or outflows, which ends up changing the tilt angle distribution of sunspots. So Lakshmi is going to give a talk, I think in this session or the next session, providing the first observational evidence of this nonlinearity in action on the sun. Okay, so if you look at the nonlinear dynamics of the system and do simulations, you will realize that this stochastic perturbations, which are produced by the convection zone, are actually more important in highly nonlinear regimes. And this is because when your dynamo number of forcing is pretty high, any random kick in the system can, in principle, move the state of the system by quite a distance in the phase space, right? Okay. And this has been studied in the context of the solar dynamo mechanism. So if you look at how the dynamics of the cycle behaves, if you increase the dynamo number, which is on the x-axis here, you see that on the y-axis you have the cycle energy, which is really the square of the amplitude. What you see is that initially when the dynamo numbers are small, you have the singly periodic solutions, and then there's a period doubling bifurcation when the dynamo number is increased. And when it's further increased, you have another period doubling bifurcation, and eventually at very high dynamo numbers, the system becomes completely irregular. And it's claimed that in that regime, there is a complete loss of predictability. The problem here, of course, is that you don't quite know, sitting here, what regime is the sun working in, right? I mean, essentially, that's kind of a bit of a free, free parameters there, although you have a good handle on the differential rotation and to some extent from the Joy's law on the alpha effect as well. Okay, so now you can ask the question that what if the dynamo is in fact in the chaotic regime, highly turbulent, highly nonlinear? Can you still make predictions? So Tobias and Bushby looked at this problem, and what they did was they created a dynamo model which was nonlinear, and then they initialized the system in slightly different initial conditions, and they eventually figured out that if you run the dynamo system for a while, the solutions diverge. They utilized this to claim that you absolutely cannot make any predictions for the sunspot cycle. I'll come back to this, but this is in fact not new, right? I mean, this was already recognized by Lorentz in his classic paper in 1963, which was basically providing a model for convection in the context of weather on Earth. The question that we must then ask ourselves is predictability at all possible? And even if long-term predictability is ruled out, can you make short-term predictions? And if yes, why? And how short? What's the time window for the prediction, right? Okay, so if you look at the dynamo equations, and these are the sort of the alpha omega dynamo equations, which is relevant for the sun. I'm not going to go into details of this, but just classify these terms into certain different categories. So most of these terms are actually flux transport terms, which are terms where differential rotation is involved. These are completely deterministic. Okay, deterministic in the sense that we think that there is not much fluctuations or stochasticity or perturbations in this kind of terms, and these are more to do with the passive transport of magnetic flux. And typically, this would delay, introduce a time delay in the system, which corresponds to the flux transport time scale by the plasma, which introduces a sort of a dynamical memory in the system. So the toroidal field source, the differential rotation which produces the toroidal field, the omega effect, is also thought to be deterministic. It's not random. However, the poloidal source, which depends on either the mean field alpha effect or the Backward mechanism, is known to be stochastic, and this is because of the imprints of the convection zone on rising flux tubes or on helical convection twisting loops of toroidal fields, right? However, the poloidal field, after it's generated, is actually observed. The R component of it is observed in the radial field in the solar surface. So in principle, you have then a handle on the poloidal field evolution equation, because you can actually replace that in the poloidal field evolution equation, and then use that poloidal field in the toroidal field equation to reduce the system to a sort of a system that you can now use to make predictions. And if I sort of mathematically reduce this, it will reduce into a time delay system of equations, in its barest form, where the amplitude of the next cycle, which is, let's say, B phi, the toroidal field, depends on the poloidal field of the previous cycle at minima, and that's the time delay, T minus T0. And T0 is the dynamical memory in the system, and one then needs to figure out that what, in fact, characterizes and determines this memory in the system, which is T0, because your predictability is only possible over this dynamical time delay or memory in the system, which is governed by flux transport dynamics. Now, if you look at the sun's interior, there are various processes for flux transport dynamics in the interior. One of the more famous ones and the more sort of controversial ones, because it's such a weak flow, is the meridional circulation. But it's also it's a large-scale circulation which couples the solar surface to the interior of the sun, and it's thought to play an important role in the Backward mechanism. All the more recent results are showing that there are other transport processes which can take over the role of meridional circulation. Nonetheless, it's thought to play a very important role, and it's a very weak flow, so slow flow, and it couples the convection zone at a time scale of something like 20 years. If you look at turbulent pumping, this is much more efficient and can vertically couple the convection zone, not just vertically, even horizontally. And the time scale of turbulent diffusion is typically about 14 years, comparable to the scale of a cycle. Now, there's also a process known as turbulent pumping, which arises because of stratified convection and rotation. In the presence of convection, magnetic fields are preferentially pumped downwards. And this turbulent pumping is pretty fast, and this has a time scale of something like 3.4 years, which is much lower than the transport cycle time scale, right? So many of these processes will combine together to determine the memory of a transport cycle, and will tell you what is this time frame T0 over which you can make a prediction ahead into the future, right? That is your time window for prediction. You cannot make predictions beyond that, right? So the way to figure this out actually is to perform dynamo simulations and introduce this, this stochastic perturbation of the system under various regimes of flux transport dynamics, where essentially all of these parameters are free parameters, and we change them in such a way that you can shift the regime of the convection zone from advection dominated, which is basically dominated by meridional circulation, to diffusion dominated, to turbulent pumping dominated, right? So these are studies that we have done, and what we do is, from this stochastically fluctuating dynamo simulations, we look at correlations from one transport cycle to another to kind of pin down how much is the memory inbuilt in the system. So on the left-hand side, you see models which are run on the advection dominated regime, where this very slow meridional circulation couples the convection zone over long time scales across at least 2 cycles. And what you see here is that these cycles have long-term memory, where the polar field at the minimum of a cycle not only has an impact on the toroidal field of the next cycle, but has an impact on also the cycle n+2, right? On the right-hand side, you see simulations with a stochastically fluctuating dynamo model, which is in the diffusion-dominated regime. And what you find here, that here the correlation is between the polar field at the minimum with the sunspot cycle flux of the next cycle only. So the memory has now reduced to one cycle. In fact, if you introduce turbulent pumping into the system, then you find that even the advection-dominated model now starts behaving like a diffusion-dominated model, with the memory in the system essentially reducing to just one cycle, right? So when you put all of this together, these theoretical simulations tell you that the memory in the sunspot cycle is short. It's only a one-cycle memory. The best predictor is the polar flux at the minimum, and that can be utilized to predict the sunspot cycle amplitude of the next cycle, more or less with some accuracy. And any prediction beyond, accurate prediction beyond n+1 cycle is not possible. Okay, so this ideas were gleaned through numerical simulations, and in 2014, Andres sort of analyzed long-term polar activity in this based on polar faculum measurements, and this was quite an ingenious paper, I think, because it sort of established the observational basis for the short-term memory as well, where you in fact see that the polar facula count of the previous cycle correlates only with the sunspot cycle amplitude of the next cycle. So this sort of proved that the simulations and the ideas we had developed based on this idea of a dynamical memory, and we had claimed that the sunspot cycle memory is short and only over one cycle, is in fact correct. So this was the observational evidence which sort of shores up our theoretical work on this field, right? Okay, so having done this, in the last 5 years, I was trying to break this as in trying to think, okay, if this is the case, you can only make a prediction sitting at solar minimum. Is there a way to actually extend this predictive window a little further, right? So what we realized is if you do that, then the best way to achieve that is to first predict the solar polar field at minimum using a different model, which is a surface flux transport model, which looks at the emergence of bipolar transport pairs and then utilizes plasma transport processes on the solar surface to generate the polar field. Then use the output of the surface flux transport model, which produces the polar field, as input in a Dynamo model to do further simulations to predict the next sunspot cycle. And using this, you can actually increase this predictive window to almost a solar cycle timescale, like 10 years. And you can make this prediction sitting at the maximum of a previous cycle, right? Okay, so now I'm not going to steal the thunder out of Prantika, who's going to give a talk on this aspect. So what she has done is she has performed the first, I emphasize this, the first century scale data-driven simulation of solar activity, coupling a surface flux transport model with a Dynamo model, which reproduces the past activity level reasonably well. And utilizing this model, she has made a prediction for sunspot cycle 25, which was out, I think, a year back. And she's going to talk about details of this. So I'll stop here in terms of our work on the sunspot cycle. So just to summarize the progress in the last 10 years so that you take this away, and this is important for the community to take away, because I realize that following the debacle of with this diverse predictions of sunspot cycle 24, there was a loss of faith in this community, right? Now, let me summarize the progress in the last 10 years. So is it possible to predict the solar cycle? I think we have reasonably established based on theory, yes, and also based on observations. It has been proven that there is a one-cycle memory, and you can utilize this to make predictions. Why? This is because of the presence of this dynamical memory. What is the best proxy for prediction? This is the polar flux at previous cycle minimum. And this, in fact, was acknowledged even a couple of decades ago. This was known. And what can you predict and how accurately? So you can predict, in fact, the sunspot cycle amplitude as well as its timing. And how accurately depends. You can calculate the uncertainty in these predictions by making ensemble forecasts, like what is done in the climate modeling community. And in fact, this is, we have done that. And how early can you predict? So based on this sort of new concept, we can extend the predictive window to about 10 years. So sitting at a solar max, you can, to a reasonable degree, predict what is going to be the amplitude of the next sunspot cycle. What is the early outlook for sunspot cycle 24? So this is going to be a weak but not insignificant cycle, and there is not going to be a Maunder minima as claimed by some folks. All right, now let's shift gear from here to the sun's corona. The sun's corona is different because the sun's plasma beta, the plasma beta parameter there is lower than 1, which implies the magnetic pressure dominates the gas pressure. And it's the evolution of the magnetic fields which then govern the dynamics of the corona. Now, of course, one important thing is the magnetic Reynolds number is still high here. So plasma flows are still coupled to the magnetic field, as in the interior. Except that instead of the plasma flows jostling around the magnetic fields, here mostly you have the magnetic field evolution which moves around the plasma, because the plasma is still coupled to the magnetic field. And it is believed that this coronal magnetic fields are driven or stressed to higher energy states by the photospheric foot point motions, where the legs of these magnetic fields are rooted, and the overlying fields subsequently relax through different states of force-free equilibria quasi-statically, sequentially reducing the energy in the system. And this is sort of accompanied by the evolution of the magnetic field as well as magnetic reconnection in the corona, which gives rise to much of the dynamic activity, right? Okay, so now why is it important to understand the coronal field, and what is the challenge there, right? Okay, so I mean, it's kind of preaching to the choir here, but let me just repeat that the coronal field is in fact responsible for coronal heating. It is responsible for structuring the global corona. It is responsible for spawning solar storms. And in fact, the coronal field is the lower boundary to the heliosphere. That is the importance of the coronal field. The problem is that the corona is very tenuous, and the photon flux that you have from the corona is very low. And typically, if you try to observe the corona, you're essentially completely, first of all, washed out by the high photon flux from the surface, and then you need highly sensitive polarimetric measurements to get a handle on the coronal field, and it is a huge challenge, right? Right now, we don't have any systematic observations of coronal fields that exist right now. Okay. However, facilities like DKIST, Aditya L1, VLC, the variable emission line coronagraph, COMP instrument from HAO, which is, I think, undergoing some refinement right now, are going to change that, hopefully, in the near future. So in the absence of good constraints on the coronal field, and even if there were, I think it's important that you develop models to understand how the coronal field is structured and how does it evolve. This has been going on in the community for a long while. In India, nobody really was doing global coronal field models, and we wanted to kind of get into this to develop capabilities both to understand the sun's corona from a fundamental level, as well as to support the Aditya mission, and in general to create an expertise that didn't exist in the country, right? However, one thing that is important is that for realistic modeling of the sun's corona, the lower boundary, which is the photospheric surface, the magnetic field distribution there is crucially important, because that really governs the dynamics of the corona, because that's where the driving happens, right? And this actually, in fact, is a problem, right? This is a problem because you have a good understanding of the surface field distribution up to about mid-latitudes, but if you go to high latitudes, because of projection effects, the high latitude fields are not very well observed, right? So if you go to the sun's poles, for example, that's a problem with current observations either from the Earth or from satellites which are in the plane of ecliptic. You really cannot get a very good handle on the high latitude fields. So in the absence of this, you need to find out what are good ways of circumventing this sort of compromised field structures in the high latitude regions to develop good boundary conditions for driving coronal field models. Okay. In fact, there are some observations of the sun's polar regions from Hinode and as well as SDO, and you see that they're highly structured and these strong magnetic field structures, and certainly not a kind of a uniform polar cap that is often most assumed, and there is a lot of dynamics going on that we're missing out, right? Okay, one of the important ways that you can actually circumvent this problem is to utilize this data assimilated surface flux transport models, where you incorporate the active region emergence below 40 degrees latitude where they're seen to emerge, and then use flux transport processes to evolve the surface field to generate a more accurate representation of the field distribution, including in high latitudes, right? So we sort of developed a kind of a concept where we decided that, okay, since we have this kind of models, we would like to utilize this as boundary conditions to develop coronal field models where you can use these models for figuring out the global structuring of the corona and making predictions, right? So our first attempts were utilizing the surface maps with potential field source surface models, and we are also developing a magnetofrictional model. But we have tested this idea against eclipses, and we made our first prediction for the 2017, 21st August 2017 Great American Eclipse. And what we see here is that using this sort of methodology, we predicted the two large-scale streamers, their locations accurately. We also, in fact, predicted the pseudo streamer on the right-hand limb of the top limb of the sun, which in fact was missed out by the predictive sciences Inca group. They couldn't predict the pseudo streamer there. What is important to realize here is that their coronal model is way better than ours. Way better than ours. We are using a drastic potential field approximation for the corona. They're using a full MHD model. The reason I'm making this comparison is to drive home the point, and this is important, that the bottom boundary that you're using to drive these models can be more important than how complex is your coronal model itself, right? If you use a good representation of the high latitude field, you could catch that high latitude pseudo streamer. And if you don't use that and use the HMI magnetograms only, then you would miss out high latitude features in the global corona. So you've gone ahead and actually made 3 predictions for 3 different eclipses now, and I request you to look at Mourinho's poster, who's going to talk about this in more details and our predictions for the 3 different eclipses. And what we find is that we are being able to reasonably predict the sun's coronal structure. What is important, and this was something that was something new, is that we can make these predictions about on the scale of a solar rotation. So we can make these predictions, at least 20 days in advance, if not more, at least during the solar minimum, near minimum. And the reason we are being able to do this is that the slow surface flux transport processes on the sun's surface are in fact building up a memory in the coronal field as well, right? And this is something that was new, that is being appreciated in the field right now. And this is important from the perspective that if you render the surface fields well, you can also render the coronal fields well. And the coronal fields, in fact, also govern the open flux evolution through which CMEs propagate. And in fact, Shonchita here is going to give a talk showing evidence that the geo-effectiveness of magnetic flux ropes are in fact dependent on the background open flux that is governed by the coronal fields. And this is because of magnetic reconnection, erosion of the magnetic flux of these magnetic clouds due to magnetic reconnection with the ambient heliospheric flux. Okay, all right. Finally, how much time do we have, Kandu? 12 minutes. So let me get through this and try to do this quickly. Star-planet interactions. Going beyond from all of this, from the origin and evolution of solar activity to its impact in star-planet systems. In the background, what you're seeing is rendering of the magnetic field lines and density of the space environment around Earth, including the Earth's magnetosphere, which has been perturbed and is reached steady state by the solar wind. These are simulations that have been performed at SESI. This is sort of a capability we're developing over the last 3-4 years. We had our first publication last year on this. Again, the motivation of this was twofold. One of the motivations was, again, to look at complementing the observations from the Aditya L1 solar observatory. The second was completely different, which was to take understanding from the solar system and utilize these models in exoplanetary systems to look at how the activity of stars impact the evolution of planetary atmospheres and what it implies for habitability. So the relevance of these simulations are wide-ranging, from the solar system to exoplanetary systems. What is important to also note in the perspective of the solar system and the evolution of the Earth is that we share an ecology, sort of an ecosystem with the parent star. And this is true for every exoplanetary system, right? And how you evolve, to some extent, is determined the evolution of the star, the parent star that is, that you are orbiting, right? And stars evolve. And even if I don't talk of the big astrophysical picture, if I just talk of the main sequence, typically in the main sequence when stars are active and you have a hot corona, you have a stellar wind. And the stellar winds typically take away sort of magnetic fields and also some amount of plasma, and so there is a loss of angular momentum and stellar spin down. And this, in fact, impacts the activity output of the star as well, which can be manifested in its magnetic output. So for example, stellar X-ray flux is a very good proxy for the magnetic flux, and this is the work we did long back. We were trying to look at how does the activity, the magnetic activity of a sun-like star evolve over age. And over this 10 billion years of age, we found that there is, in fact, a power law decrease. This is a log-log plot in the magnetic activity output of a sun-like star, which tells you that when the sun was younger, the activity of the sun would have been much stronger, and it would have much more frequent flares, stronger winds, and stronger radiation, right? And this has also been now actually directly observed based on this technique of Zeeman Doppler imaging by others, that the magnetic activity level actually falls in solar-like stars with age, right? So then this tells you that the young sun was much more active, and there are other stars which are faster rotators, which are much more active stars around which there are exoplanets, right? And then there was this work by in fact, the group of Shibata-san, who looked at stars at different rates of rotation and ages. And what they found is that stars could have flares which are about 10,000 times stronger than the strongest flares that have been observed in the sun. And this could have very serious and dramatic impacts on the atmospheres of planets or exoplanets. More recently, last year, a group from India, Physical Research Laboratory, looking at a meteorite which had fallen in Russia, found evidence of a solar superflare when the sun was very young, which is in fact the first evidence of a superflare on the sun, right? Now, these are important because this tells you that the magnetic activity level, the stellar wind output varies, and this variability can in fact impact stellar planetary atmospheres. So these are simulations that we have done at SESI with our star planet model, where we've done a parameter space study to look at the impact of stronger winds on the magnetospheres of planets. And what you see here is that when the wind speed is actually made stronger, going from like solar wind speed to about 8 times the solar wind speed, the magnetosphere magnetopause in fact starts shrinking and moves closer and closer to the planet. What this implies is that if you're in an atmosphere and you have a strong wind, then the magnetosphere will shrink and the atmosphere will be exposed to ablation due to viscous coupling between the solar wind particles and atmospheric particles, and it can actually erode away the atmosphere of stars. And you see this actually in effect. When you do these simulations, you can put tracers, passive tracers in the atmosphere. You can trace the mass loss. And we have done this, and this is sort of described in the work that we published last year in ABCE, where you can see the impact of atmospheric mass loss because of the interactions of stellar magnetized winds with planetary magnetospheres. More recently, we were approached by the Chandrayaan-2 mission team because they figured out that there is not much understanding of the lunar space environment, and they were getting this kind of very, very variable sort of energetic particle fluxes which they're not expecting in the magnetotail around moon. And so we initiated this star-planet-moon interaction simulations, where on the left-hand side you see the whole system. There is the Earth and there is the moon, which is really small. On the right-hand side you see the moon zoomed in. And you do find nice current sheet structures and density perturbations being generated when a solar wind shock moves through the lunar environment. And in fact, this also changes the large-scale connectivity in the magnetotail, with connectivity is established from the lunar exosphere all the way to the Earth's poles. And if you look at 1970s or 80s, there are claims that the aurora in Earth is sometimes governed by the lunar passage. And this is interesting, and now we sort of know why that happens. So Arnav Boshak and Ranadip Ghosh-Dastidar have posters which are describing this new initiative that we are building here in India to do star-planet interactions. And I encourage you to go and look at their posters to figure out what we can do in terms of modeling both the solar system as well as exoplanetary systems with this capability. Okay, so these are my concluding remarks. So understanding solar stellar magnetism is, from the fundamental perspective, a fascinating, area of research in itself. And this sort of brings out the best in MHD in the sense that you can, in principle, every MHD process, you find a manifestation of that in the solar system, right? And this sort of provides a window to the magnetic universe. Okay, this understanding is relevant for exploring how active stars shape their astrophysical environment and what this implies for the atmospheric evolution of habitability of planets. And most of my research has been driven by this sort of motivation to push this models to make predictions and then sort of confront them with observations, try and come back and refine the physics. And I think this is sort of a important way of working if you are a theoretician or a modeler when you have so much data. I will leave you with a concluding teaser. So, do you believe that the transport cycle 25 has started? Okay, if you want to form an opinion about this, go ahead and look at the poster of Aditi Bhatnagar and Sanchita Pal. Okay, and with that, this is my last slide, acknowledgements, and I'll just leave it there, saying that in the last 10 years, contributions from my students have been fundamentally important in driving what I think. They have more expertise in various domains than I have, and this has been really, really helpful. So thank you to many of them, who are here and who are not here. I think to some extent, much of this award actually owes to the work that you have done. To my colleagues at IUCA, IIA, PRL, ISER, Pune, ISRO, including Durgesh, Shankar, Prasad, Dipankar, who are here, Nandita, who are not here, for helping us establish SESI and standing by us all these years while you're developing all these capabilities. And of course, family and friends and the Ministry of Human Resource Development, Department of Science and Technology, and ISRO for funding the work that we have described here. Thank you.
Thanks for the very good talk and congratulations on my behalf.
Thank you.
So I have a comment and a question on the first part of your talk where you talked about the solar dynamo mechanism. So you were talking about observational evidence for the Babcock-Clayton effect and also theoretical evidence. But there is also a third class of evidence, namely numerical evidence, because there is an increasing amount of simulations that actually do direct solutions to the MHD equations instead of the mean field description. And if not all, at least in the majority of these models, we actually measure an alpha effect which is not concentrated near the surface, more consistent with the distributed picture. And even then, we can go beyond that, and we can even measure all these turbulent transport coefficients, not only the alpha effect, but turbulent pumping. And in all cases that we measure these things, we don't get a situation where the turbulent pumping would be significant and the alpha effect not. So just a comment that there is this evidence, and how would you now react to this, this evidence?
So this is an important point. The point she's making is this, that there are also this direct numerical simulations of magnetoconvection, and this produces all these different transport coefficients, including the mean field alpha effect, which can be extracted out of the simulations. How do they compare? What is the context with this kind of simulation that you've done and with solar cycle predictability? Okay, let me take you back to this plot here. This uses a mean field alpha effect, which is a baseline, but it doesn't vary. The mean field alpha effect is required because you have also shown that if the dynamo slides into a model like minima, there is no way a Babcock-Clayton model can take it out. You need the mean field dynamo alpha effect, right? However, the variability in this system is only due to the Babcock-Clayton mechanism, and that explains the observed variability pretty well in the last 100 years. So my challenge to you, in fact, not to you, but this is a challenge to all of us, is to figure out why are manifestations of the Babcock-Clayton mechanism not emerging out of direct numerical simulations. This is a problem that has been fascinating me. In fact, I was talking to Axel last year when I was in Nordita. I think we have to move the DNS in a way that we can somehow assimilate the Babcock-Clayton idea into there and have an interplay between these two different ideas. This is something that we have to start now so that we can actually, in fact, produce tilted bipolar transport regions, which then sort of produce this phenomena which is observed on the solar surface, the flux transport that is observed on the solar surface, which then recreates the polar field. This is something that has to be caught within these direct numerical simulations. This is important.
Can I make a short comment? Very short. So thanks, that's a very important point. But to me, actually, the Babcock-Clayton effect and the rotationally influenced convection are just one and the same effect working on different scales.
Okay, so then we are not arguing about anything. Then. We're on the same boat then.
How does one choose what is the turbulent pumping that you use?
Right. So this is not very well constrained. So there have been papers by Steve Tobias, 2001 ABG, I think if I remember correctly, also by Petri or Marit, I mean Skapila, certainly, 2-3 papers in ANA, where they've tried to extract this from numerical simulations. There's no direct observations, of course. So typically the speeds are on the order of something like, 10 meters per second. This is from the simulations. I wonder whether you could actually make an estimate of that at least near surface based on how quickly the flux is being recycled and submerged. Because the effect of that is in the submergence of flux, right? And this is something that is in principle observable. So one can in fact set a constraint on this, but only at the surface, not deeper down.
Just a comment on that. If you do a closure calculation, and you'll find it in Axel's and my review, you'll find the turbulent pumping term related to all the other coefficients, including an omega cross gradient effect.
Right.
Divyendu, are we going to get a unified solar cycle prediction, or it's basically for example, for each prediction, actually a group of people come up with saying that the cycle is going to be strong, and a group of people come up with
I am not responsible for that. You are responsible for separating out the junk from the physics. And this is a role that we must all play, not just in science, but also in our society.
Last question.
It's a comment, so I would agree with you. So some helioseismologists would say that before the measurements from helioseismology, that people really didn't know what was the depth of the convection zone because it ranged from 20 megameters to 200 megameters. But Sprout's convection zone model essentially had it right in within the error bars of helioseismology.
Yeah.
I think we have to move on, and please ask many questions to Divyendu. Don't let him alone afterwards.
Thank you.
Then?
Do you have this one?
So the next speaker is Bidya. What are you going to talk about, Bidya? Okay, I got this. Oh, you have something. Yeah, it's going to talk about bipolar magnetic region tilts and the Babcock light and dynamo. All influenced by Arnab, no doubt.
Okay.
Okay, so it's a great pleasure for me to give this presentation just after this prestigious award lecture, and I thank the organizer for making this arrangement. Okay, so as the title says, I'll talk on bipolar magnetic regions, tilt, and the Babcock latent dynamo. So I begin my presentation with this magnetogram. So here you see some bipolar magnetic regime, BMR. And this BMR have tilt with respect to this east to west direction. And this tilt is very crucial for the generation of poloidal magnetic field that we see on the surface of the sun, okay? Which is the original idea of Babcock and Leighton given in 60s. So essentially, in this process, when this BMR decay and disperse their magnetic flux, the one polarity flux try to come close to the equator and cancel with the opposite polarity flux from the other hemisphere, and the other polarity try to go to the pole. Okay, so this is better seen from a movie. So this is a movie from a kinematic dynamo model. So we are seeing the surface of the sun where we deposit two bipolar active regions, and they have a little tilt with respect to this east-west direction. And because of this tilt, I'll show that when this spot decay, they will produce a magnetic field near the pole. So this is a kinematic model. So the turbulent diffusion is given as an input, and then differential rotation is also given. So that's why this equatorial region rotate faster than the high latitude. And there's also a large-scale Mourinho flow that goes from equator to pole on the surface. Okay? So it tries to drag the field towards the pole. So you see that at the end, we see some magnetic field near the pole, which is the poloidal magnetic field. So you see dipole-like magnetic field. So red is the field that is pointing outward. So we get a dipole-like magnetic field just from the decay of these two BMR. Okay? And this is possible because this spot have little tilt. Okay? And if this spot do not have a tilt, then we will not get anything. Okay? So their flux will cancel each other. So this tilt is very crucial for the generation of magnetic field on the surface. And this tilt follow a relation called the Joyce law. So it says that the tilt of the sunspot is equal to some constant and then sine of the latitude of the spot. Okay? And so this is the popular Joyce law. Okay? However, if you see the individual BMR and plot its tilt as a function of latitude, then we get this very dirty plot. Okay? So you see a lot of scattered. Okay? So it's very difficult to even identify the Joyce law, okay, from this plot. So you see a weak trend, okay, and there's a huge scatter, okay, around this relation. So this Joyce law is valid only in a statistical sense, and there's a huge scatter around this this relation, and this scatter actually roughly follow a Gaussian distribution. So if you combine all the data, then you will follow a good distribution which follow roughly a Gaussian distribution with a sigma about 17 degree. Okay? So this scatter play a very important role in changing the poloidal magnetic field in the sun. Okay? Because on an average, sun produce only 1 or 2 BMR per day. Okay? So as the number is very less, we expect significant effect in the poloidal field. Okay? So this scatter, tilt angle scatter and its effect we can see from the observation. Okay? So you can see this its effect in the observed magnetic field. So this shows the radial magnetic field distribution as a function of latitude and time, and we see frequent polar surges of opposite polarity field. So for example, in this hemisphere, we see the magnetic field is expected to be negative, the blue color, and we see a clear evidence of positive polarity field, the red color. Okay? So this is actually caused by the wrongly tilted BMR. Okay? And we see this evidence in all the solar cycles. There are frequent evidence for that. Okay? So the scattered in BMR tilt is the cause of the variation in the polar magnetic field. And in fact, if the tilt is large, then it can suddenly reduce the polar field. And that change in the polar field is going to affect the next solar cycle. Okay? As Dibyendu explained that this polar field is the seed for the next cycle, and so any change in the polar field will be reflected in the next cycle. Okay? Okay, so when you include this idea in a kinematic dynamo model in which one important source of the generation of poloidal magnetic field is this decay of the sunspot, and if you include this tilt scatter in this model, then we can reproduce a variation in the solar cycle that we see in the observation, including the variation that we see within the cycle, okay? Like the double peak and dip and or spike. Okay, so this double peak, which is popularly known as the Genesee peak, are directly produced from the scatter in the tilt angle. Yeah? Okay, so the next question is how these BMR are produced. Okay? So it is, generally believed that BMR are produced from the toroidal magnetic field, which is rising from the interior to the surface through magnetic buoyancy. Okay? And so if you imagine that if you have a toroidal magnetic field pointing in this direction, and if a portion of this field rise to the surface, then we get a bipolar, then we get a BMR here with the magnetic field pointing outward here, and here the magnetic field should be pointing inward. Okay? And you see that all the BMR appearing in this hemisphere have the same type of polarity. So this picture nicely fit with this observation. And as you see this, in the northern hemisphere, the BMR's polarities are opposite with respect to the southern hemisphere. So we can predict that the toroidal field must be opposite in this hemisphere. Okay? So if the field is pointing in this direction, and then if portion of this field rise through magnetic buoyancy, then we get BMR of this pattern. Okay? Okay, so then the question is, how do you get the tilt in the BMR? Okay? Now, we do not have a very well-established theory for the generation of the tilt in the BMR, but this thin flux tube model nicely explains the variation of tilt that you see on the surface. Okay? So in the thin flux tube model, we know that the toroidal magnetic flux, the flux tube of the toroidal magnetic field, they rise due to magnetic buoyancy, and during its rise, some diverging flow will produce. So the plasma will try to actually diverge. So this plasma acquire a azimuthal flow. Okay? And the Coriolis force acting on this azimuthal flow gives a tilt, gives a basically torque, and that torque is causing this tilt. Okay? So the Coriolis force acting on this diverging flow on this rising flux tube gives a tilt, and this explanation nicely reproduces the observation, the Joyce law. Okay? Okay, so in this picture, you expect that if the magnetic field in this BMR forming flux tube is strong, then the magnetic buoyancy is strong, so the flux tube will rise quickly, so the Coriolis force gets less time to tilt. Okay? So the tilt should be less if the magnetic field strength in this flux tube is less. Okay? And in fact, this thin flux tube model gave a very nice formula. Okay? So the tilt is proportional to the sine lambda, which is Joyce law coming from this Coriolis force. Okay? And then this magnetic field dependence, okay, in this flux tube. So magnetic field strength is large, then the tilt should be less. Okay, it's nicely understood. Okay, so motivated by this observational fact and this theoretical idea, we try to explore this BMR features from the observation. Okay? So we analyze the MDI data which is available from 1996 to 2011, and HMI data from 2010 to 2018. So we actually need the line of sight magnetogram data and the intensity continuum for our study. So to detect this BMR, we essentially followed the method which was used in Stenflo and Kosovich 2012. So in this method, so essentially we do, there's a threshold for, to detect the magnetic field strength first, and then we give a moderate flux balance condition so that we do not pick up the unipolar BMR. Okay? And then to reduce the projection effect, we restrict ourselves up to about 0.9 solar radius, and we also exclude the BMR that have absolute longitude above about 50-degree longitude. Okay? And all the analysis has been done by this very bright young researcher, Vibhuti Kumar Jha, and who is in the audience. Okay? Okay, so now I show the result. Okay, so this shows the distribution of the BMR magnetic field. Okay, so the magnetic field in the BMR and it's actually its distribution from the MDI data. Okay. So now you see so there's no monotonous distribution. So we see a clear peak in this distribution, two clear peaks in this distribution. So one peak is around 2 kilogauss, and another is around 0.5 kilogauss. Okay? And this similar behavior also seen in HMI data. Okay? So HMI corresponds to a cycle which is weak, the last solar cycle, and that's why we see less number of strong BMR. Okay? So that's why this peak is little less. Okay? But we see similar distribution and similar property. And when you explore this data more, then we find that the BMR corresponding to this smaller magnetic field strain, they corresponds to BMR which do not shows sunspot in the intensity continuum. So we also see the intensity continuum, and then we see this BMR, which appears in this in the low magnetic field range, and we see that they just seen only in the magnetogram, not in the intensity continuum. So basically, they are not seen as a sunspot. Okay. On the other hand, this BMR, which have strong magnetic field, they are also seen in the intensity continuum. Okay, so we call them BMR with spot, and this guy you call BMR with no spot. Okay, so this is very surprising, features that we got, that to separate basically two classes of BMR, and surprisingly both of this BMR follow a similar latitude time distribution. Okay, the same type of butterfly diagram. Okay, so there is no latitudinal preference in this smaller BMR. So you cannot expect that this smaller BMR actually coming from small scale dynamo or something. So both are actually coming from a same type of large scale magnetic field. Okay. Okay, so next we explore their Joyce law variation. Okay, so the Joyce law is gamma equal to some constant in the sine lambda. So we analyze this Joyce law in each magnetic field bin. Okay, so we bin the data based on the magnetic field strength, and we compute the Joyce law. So here we show this amplitude of the Joyce law, gamma 0, so that we just ignore this this latitude dependence part. So we see the strength of this Joyce law, the amplitude of Joyce law has some magnetic field dependence, okay? Magnetic field in the BMR. So you see initially it increases little bit, and there is a little decreasing trend, okay? In both the data, okay? Both the data actually show some difference, but we see similar trend in both the data. Okay, this is as a function of magnetic field strength. This is as a function of the magnetic flux in the BMR, okay? Okay, so as I said in the introduction, that from the thin flux tube model, we expect the magnetic, the BMR tilt should decrease with the magnetic field strength. So at least in the high field regime, we see a little evidence of the decrease of magnetic field, decrease of tilt. Okay, and so this decrease of tilt with the magnetic field strength is actually, we call it a tilt quenching. Okay. So actually, in all the kinematic dynamo model, we need a quenching. Okay, we need a nonlinear quenching, because kinematic dynamo model doesn't include any nonlinearity. So the magnetic field will increase with time. So we need a quenching, and that we put by hand. Okay, we put a quenching of this form. Okay, so in this, or maybe in the tilt, we just put this quenching. Okay, so at least we see some evidence. Okay, but our data is limited, so we cannot actually make a very strong comment in this. We do not have a good result, but at least we see some evidence, and so this is very encouraging at least. Okay, so then we also study the scattered around the Joyce law. Okay, so as I said, the tilt follow a Joyce law, and so this shows the scattered as a function of magnetic field strength in the BMR, and this is as a function of magnetic flux in BMR. Okay, so these two results are very promising. So again, this picture nicely fit with the theoretical idea that in the thin flux tube model, the toroidal magnetic flux tube rise in the convection zone, and during its rise, the convection actually disturbs this flux tube and gives a scatter. Okay, and if the magnetic field strength is strong, then we expect that the flux tube will rise quickly, so the convection get less time to disturb the flux tube. So we expect less scatter if the magnetic field strength is strong, and also the magnetic field tension also increases, so convection will have a less chance to perturb. So the scatter should decrease with the increase of magnetic fields. Okay. Okay. So here are my conclusion. The scatter in the BMR is the main cause in the variation of the solar magnetic field on the surface, and it can nicely explain this double peak in the observed solar cycle that we popularly call the Genesis peak. Okay, and this magnetic field distribution of BMR is bimodal, and then the tilt and the scatter of the BMR decrease with the increase of magnetic field strength in the BMR. The reduction of tilt with the increase of magnetic field gives an indication of the nonlinear quenching that we routinely use in the kinematic Babcock-Clayton dynamo model. Okay? Thank you.
Nice talk. As you told, your data is limited. So can it be extended some like other data?
Yeah, I mean,
Yeah.
in fact, we want to do, I mean, this,
Mount Wilson or
yeah. So
yeah.
we also use the Mount Wilson data, and the problem is Mount Wilson data are not, I mean, good. I mean, in terms of
resolution,
quality.
and,
Yeah. So we also explored the Mount Wilson data. Okay, although we did not actually so, but we see some trend. Okay, so we see some decreasing trend. We do not include this in the paper. Okay, so actually we need good data. I mean, at least the data from the high, from the strong cycle, because we need data in the high magnetic field regime. Okay, so when we see this little evidence of the quenching, okay, and we need a BMR of strong magnetic field.
Yeah. Okay. Thank you.
Okay, I think we should move on. Thanks to Vidya. Some more.
Yeah.
The next talk is by one more of Arnab students. Okay, past student, Gopal Hazra, and he's going to talk about one of the topics that Dibyendu left off, the influence on planetary atmospheres.
Hello everyone, so my name is Gopal Hazra and I am a postdoctoral researcher in Trinity College Dublin, and I am not going to talk about the generation of the magnetic field, rather I am going to talk about that how the magnetic field can impact on the stellar radiation and the corresponding effect on the exoplanetary atmosphere. So basically in this talk I am going to talk that how the study of sun can help us to enhance our knowledge about the exoplanet. So let me start with, oops, sorry. Oh, okay, so I'll just, yeah, so let me start with the exoplanet Ju. So in this plot I am showing this so far discovered exoplanet. So in that plot I am showing this the size and the distance plot. And so far we have like more than 4,000 exoplanets have been discovered, and almost 25 to 30% of this exoplanet have a solar-like host star. And we find that many of them have like cyclic magnetic activity. So in that plot, what we are showing is the distance of the planet from the host star, and this is based on the size of the planet. So if you see this plot, based on the size of this planet, we divide this whole exoplanet, discovered exoplanet in hot Jupiter, cool Jupiter, and the super Earth. Now observationally, since hot Jupiter are like very easy to detect, so we are mostly concentrating on this hot Jupiter area. So here I am just showing a typical hot Jupiter system. So this is the host star, and this is the hot Jupiter with its atmosphere. So if you just see this, when they are like very close in, so the distance between this host star and this exoplanet is almost 0.05 or 0.03 AU. And in this case, most of the stellar radiation which is coming from the host star, they are like going to affect this atmosphere. And in most of the case, this stellar radiation comes from this host star and ionize this hydrogen material of the atmosphere and helps that atmosphere to escape by a planetary outflow. So that's why this studying this stellar radiation is very important for this hot Jupiter. And we have some observational evidence for that. So if we just observe this Lyman alpha or H alpha from this atmospheric escape, then we see the mass loss rate is almost 10 to the power 8 to 10 to the power 11 gram per second. So it indicates that the heavy mass loss rate is helping the atmosphere to escape from the planet. Now the whole part of the radiation is not going to affect the atmosphere. It is mostly the X-ray and the extreme ultraviolet part, that is we shortly call the XUV fluxes. So that is going to affect in the atmospheric escape, because the since we assume this atmosphere are mostly like hydrogen based, so we need the radiation which has the ionizing potential more than the hydrogen ionizing potential. And another important part is like this getting X-ray and this XUV from the host star is like very difficult to observe, so we mostly concentrate on the sun so that we can get some information that how the XUV fluxes from sun like behaving with cycle with time, so that we can get some information about that, and we can extrapolate that information for the other stars. So let me just start with a system, sorry, just this is the hot Jupiter. And here we assume that the star like a hot Jupiter is orbiting around a sun, and since sun has a like magnetic cycle, so we just ask ourselves this question that whether this magnetic cycle is going to affect this XUV radiation, and if it does, then how it is going to affect the mass loss rate, and how it is going to change this atmospheric escape. So for that we use a planetary wind model, and in this planetary wind model we just solve this momentum equation, energy equation along with this ionization equation, assuming this the mass is conserved in this case. So we solve this all equation in a steady state. So momentum equation, you see the gradient of the velocity is mostly balanced by this pressure gradient, planetary gravity, and the centrifugal force, and the resultant like the tidal force, resultant gravity difference between the star and the planet. For the energy equation, the internal energy, the change in the internal energy of this atmosphere is like balanced by this PDV work, like when the gas is expanding, so how much energy is generating, and the successive heating and cooling term. So in this equation, if you see this heating, this Q is like mostly coming from the stellar radiation, and this is the optical depth. So how much stellar radiation can be absorbed in the atmosphere, it is defined by this heating term. And then we solve this ionization equation. So now when you have a cyclic variation, so if this XUV varies, so that means it is going to change this whole energy equation. So that correspondingly change this velocity, temperature, and the whole profile. So if we see this the XUV radiation is varying, so we expect that the planetary atmospheric properties of the planet and the mass loss rate will change. So here I am showing this how we can get the XUV radiation from the sun. So in this case I am showing this stellar spectra from this timed C data. This is the NASA's mission around the 2002, and this is the thermal, ionosphere, mesosphere, energetic dynamics, and this is from the solar extreme ultraviolet experiment data. So in this plot I am showing full range from 0.5 to around 195 angstrom spectra, and I overplot with the sunspot number, and we show this solar minima and solar maxima. From that plot it is not clear that during the solar minima or solar maxima whether these ultraviolet fluxes are increasing or not. So we plot it here like with time, and since we are only interested for this wavelength from 5 angstrom to the 915 angstrom, because to ionize hydrogen we need at least incident radiation whose wavelength is more than 912 angstrom, because only that incident radiation can ionize the hydrogen. And then we almost like integrate from the 5 to 915 angstrom over this spectra, which is shown by this black line, and we plot this. So here from this plot it is like quite evident that this stellar radiation is almost varying with this sunspot cycle. So during solar maxima it is like high, and during solar minima it is less. Now if we just put this one in our planetary model, then we want to see that whether the planetary result can have different value for the in different epoch of the cycle. So for that what we do, we take this whole data from 2002 to 2018, and we just separate out this data like in a, we just make a bin after a 6-month interval, and that gives us almost 34 cases of simulation. And here I just show the results. So in the left plot we show this velocity, density, and pressure and temperature profile, and this x-axis is the distance from the center of the planet outwards to the atmosphere, and the two color defines the two epoch during solar minima and solar maxima. So if you see this velocity profile or whatever the profile, all varies across the solar cycle. So if you take the solar minima, since during the solar minima the effective UV radiation is very less, so that is going to affect the planet like not that significant way when it is solar maxima. So you can find the difference between here. And that becomes much more significant if we just plot the mass loss rate. So in the mass loss rate, if you see this mass loss rate, it's just almost following the solar cyclic nature. So during the solar maxima, if you see this mass loss rate is very high, and it is almost following. So we find that if you have a stronger cycle, so that is going to affect the mass loss rate much better way than if you have a like weak cycle. So for the data we considered, we have a 2.85 increment in this XUV flux over a cycle. So that is going to affect almost 2.5 by the mass loss rate. So this is for the solar cycle 24. So if you consider the solar cycle 19, so then this factor is almost 10 times. So that is going to affect the mass loss rate by the almost like 9 or 10 times. So that is like if the host star has a stronger cycle or this thing, that is really going to affect the mass loss rate of the atmosphere. So next we want to see that whether that atmospheric escape we can get from the transit line. So here I am showing this is not the spot, this is the exoplanet. So if planet is like transiting the transiting a host star, then you can see that there is like this is the black line shows the geometric optic. So when if it doesn't have an atmosphere, it is like only some portion of the brightness can be obscured by this planet. Now if it has if some activity is happening in the star, for example, it's like very strong, and then something strong flare is happening, then you will see there is like the atmosphere will evaporate from that. And if now we measure this Lyman alpha, we will find that there is a like big dip in this case. So whether we can get this kind of line from our simulation or not, so for that we do this ray tracing experiment. So we create like our host star as a this big band, and we tried like then we just transit our atmosphere through this planetary disk, and we want to see that how we are going to get this the spectral transit. So next, so here I am showing these Lyman alpha lines. So the black line shows the geometric geometric transit. So when the planet is transiting, so that much flux can be absorbed by this planet. But when it has like atmosphere and atmosphere is transiting, we'll see there is like this whole depth. But the problem is when we just do for the cyclic variation, we see that there is not significant amount of the cyclic variation in the Lyman alpha. So here I just show this solar cycle plot to represent our timing, that during solar maxima it's like 2002 and there is no difference. But if we just plot H alpha, in this case we see that like there is a significant variation in this H alpha transit. So that is like quite interesting to see that whether this cyclic variation we can see from the observation. So next we want to just show for the realistic system, like this we done by assuming a hypothetical system where Sun is like a hot Jupiter is orbiting around Sun, but now we want to get like a existing planetary system, for example HD 189733, and we want to see that whether we can model the cyclic variation or effect of the cyclic variation on this planetary atmospheric rate. So here I just show this for the other stars. For Sun it is very difficult to measure the sunspot number, but for other stars we do not have the sunspot number, so we need to rely on this magnetic flux or whatever we have from the GDI image. So here I show the solar magnetic field from the HMI data. It is available from 2010 to 2018, and in that case we find that the solar magnetic flux is like highly correlated with the XUV flux. So this is the magnetic flux. In blue line I show the magnetic flux and XUV flux by dotted line. So we see this is highly correlated, but this is for the high resolution magnetic map, which consists of spherical harmonics L equal to around 192 or something. But for other stars we do not have that high resolution, we have only the large scale part. So we want to see whether the large scale part of the solar magnetic field is correlated with the XUV flux or not, and we find that it is indeed correlated, it's like 0.95. Then we use this formula to get the XUV flux from other stars. So we did this correlation plot. We see the XUV flux is like almost proportional to the magnetic flux. And then we take this HD 189733 ZDI image. So this is in the 3 times. So you see the June 2006 and September 2013, there is a like huge variation. So now if we put this ZDI image in our formula, then we see that this is like creating a huge difference in the XUV flux. So this is during minima, this is during maxima. So this is like a huge variation in the XUV radiation. So now we want to see that if we put this in our planetary model, then how it is going to affect the mass loss rate. So here I show this mass loss rate. During the minimum epoch and the maximum epoch, it's like almost varying 3 times for this HD 189733. And here I show this H alpha plot also. In H alpha plot, we see there is of course there is a cyclic variation in H alpha. So there is just, I'm showing one case considering a strong flare. So if the sun has a strong flare and that has like their XUV, if I assume it is like 5 times during the cycle minima, it is also creating a heavy mass loss rate. So just to comment, like temporal variation in this system is already observed in Lyman alpha, but during our model is spherically symmetric, so we do not get that much variation in the Lyman alpha. But we expect that for more sophisticated observation can find this difference in the H alpha as well. Okay, and so I just keep with the conclusion, and I'll ready to take some questions. Thank you.
How does this compare with mass loss rates due to CMEs?
CMEs that we have not considered yet, but CME, if we consider CME, then we have to consider the interaction of the CME and the stellar wind with the planetary wind. So that I'm like currently doing. So this doesn't consider that one. So this only consists the stellar radiation, how it is going to affect the planet.
Yes, Arnab.
We know that the mass loss rate from the sun due to solar wind is just negligible compared to its mass. But in the case of this planetary atmosphere mass loss rate, over say billion years, will the atmosphere lose a significant amount of its mass or negligible?
No, it is for this hot Jupiter system. If it just loses its mass like in that rate, 10 to the power 8 or 10 to the power 9 gram per second, so it takes like few million years, like 0.3 million years or something. So for the hot Jupiter, they indeed erode this atmosphere from.
Next talk is by Alexander, and he's going to talk about magnetic energy variation in emerging active regions.
Good morning. Here is an outline of my talk. First, I will say a few words about the emergence of active regions and the direct cascade that is observed during the emergence. Then I will talk about the power spectra method, which helps us to analyze the energy distribution at different spatial scales, and our preliminary results on energy gain during an active regions emergence, and some possible predictions of flaring activity of active regions by the power spectrum method. Active regions is a place where a magnetic flux bundle appears at the solar surface. This magnetic flux bundle is formed somewhere in the convection zone, and when the buoyancy becomes high enough to lift this bundle to the surface, it starts to lift. But due to a very significant decrease of density and pressure, this bundle cannot appear as a coherent structure. It rather fragments into thin, very thin magnetic tubes, and these tubes are seen as darkening in the white light image and as small moving magnetic features in the magnetograms. So it is supposed that these thin magnetic tubes are such a serpentine line. These small elements, magnetic elements, gradually merge together to form larger elements, such as pores and sunspots. So we can assume that this inverse cascade, merging of small magnetic elements into a larger structures, is a dominant process that takes place during the emergence. By the way, the opposite process is a direct cascade, when the large magnetic element fragments or decays into smaller ones. So our question is whether this inverse cascade is a dominant process during the emergence. To find out this behavior, we use the magnetic power spectrum method. We use a line-of-sight magnetograms acquired by HMI instrument, and we find its Fourier transform. We find its spectrum and use an integration of the power spectrum to obtain one-dimensional power spectrum of active regions. K is a wave number in this case, and R is a spatial scales. So, typical power spectrum for 3 active regions, its emerging active regions are shown here. The lightest curve is almost a quiet sun, and as the emergence proceeds, the spectrum steepens and the energy increases. But actually, we cannot analyze in details how the energy increases at different scales at this plot. So we propose to use to calculate the difference of two spectrum are calculated for magnetograms separated by time. An example is active region. This active region, you can see 2 magnetograms. The time distance between them is 2.5 hours, and here we can see these small magnetic elements, and at these magnetograms, these elements are predominantly merged with this larger structure, and we can calculate power spectrum for this at time, for this at time, and find the difference between them. So we can see that the energy at small scales decreased, and at large scales the energy increased during this time. But our further analysis showed this behavior is an exception rather than a rule. We also can calculate the time derivative of the energy of the power spectrum of an active region. So here is our results for this active region. At this axis we have time. This axis is a wave number. A blue curve is a total on-site magnetic flux, and this plot is variations of the energy. So yellow and orange colors are increase of energy, and blue colors are decrease of energy at a certain scale. We can see that as the emergence begins, I guess here, we see increase of the energy at these scales, and gradually as the emergence proceeds, the energy increases at large scales only. So the main contribution of energy during the emergence is at large scales. Sporadically, we can see all the cascades. We indicated them by arrows. I see is an inverse cascade. As you can see, this blue color is decrease of energy at small scales and increase of energy at larger scales. We also can see at a direct cascade, so some dissipation take place here, and but most of the time we can see, we call it a regular emergence, when the energy increases at larger scales only. One more useful information we can obtain from the power spectrum is the power index, or simply the slope of the spectrum within the inertial range. Inertial range is a part of the spectrum where the spectrum is linear. Here's a plot for 16 active regions that shows the slope of the spectrum of our index and the flare index or flare activity of active regions. And we see that it probably exists a very good correlation between these two quantities. Another interesting thing about this power spectrum is its increase in time. I want to show you this movie. A green color is a power spectrum. This brown curve is the slope of the spectrum, and this curve is a total on-site magnetic flux of the active regions. So you can see that as the emergence starts, just at the very beginning of emergence, the slope of the power spectrum increases abruptly. You see? Well, maybe we can use this feature of the slope to somehow predict the future flaring activity of active region. We wanted to make some statistics on this issue. Here you see similar plot. A black color, black curve is the slope of the spectrum. Blue color is the total on-site flux, and as well you can see that the slope increases abruptly and just at the very beginning of the emergence. Pay attention that at this moment, when the slope is already high enough, we can see only the first imprints of the active region, of a future active region. But when this magnetogram is the maximum on-site flux. So we used data on 250 magnetograms and estimated the value of flux emergence and slope increase. This duration and this duration as well. So how quickly the slope changes and how quickly the magnetic flux changes. And here is our a plot. This axis in J's is the duration of flux increase, and this axis is the duration of slope increase. And we can see that most of active regions emerges slower than their slope increases. So maybe we can evaluate the value of the slope at this point and predict its future flare activity. It is the very beginning of the emergence of active region. So the coffee is waiting, so conclusions. Signatures of the inverse cascade are seen sporadically in during the emergence, but the dominant contribution is from emergence of large-scale coherent structures. Slope of the power spectrum can be used to evaluate and to point out the site where an intense emergence will occur. And probably, but we have to confirm it yet, the power index that increases abruptly at the very beginning of the emergence can be used to predict the future flaring activity of an active region. So, a coffee.
Thank you very much. It's finished in advance, so time for a few questions. Yes.
The increase in the slope of the power law index seemed to be coincident with the flux emergence. So you can't really use it to determine that flux emergence is going to occur, can you? It seemed to occur at the same time. It seems that this power law index is just is a proxy for flux emergence, but that doesn't tell you that that flux emergence will occur.
You will see an abrupt increase of the slope at this place of a magnetogram. We can say that intense flux emergence will take a place at this site. So, but we find any correlation between the value of the slope and some other active region values.
I was wondering why is it 2? Ox, what is the cause for slope of 2? From 5/3 you went to 2, right? I mean, the spectrum.
What shocks?
Index went from, I thought, to 2, to value of 2.
Mm-hmm. It's a slope. It's actually the slope of this power spectrum. This value is a -1 or 1 absolute value for the quiet sun, and minus and 1.7 for active regions, usually.
Okay, if no other, call the speakers of the morning. Durgesh has some announcements to make.
It's just some of you still need to pay your registration fees, so please make sure you go on the secretariat desk. There will be somebody who will guide you again to take you to the accounts. We'll break for tea. Let's keep the break half an hour. So we'll reconvene in half an hour. But for the next break, before the lunch starts, we'll take a conference photo, so don't disperse. We'll all go, somebody will guide you that where we'll take the picture. It will be in the Kund area within the main campus, and then from there we'll go for lunch. So, thank you.
do we keep online or do we keep online or we just connect again? Okay, I need a. Okay, I can stop my video for a few minutes. Oh, that's right. Yes, let me. I need a. Share. Yeah, right. I'm working on that. You see my slides? Oh yeah, I can go to the first page. Presentation mode, yes. So the audio is also good, right? Let me show you a video and see a movie of my presentation and see how that works. Does it show? Okay. Nice. Yeah, I see something in white. Somebody in white. So it's about 15 minutes from now, right? Okay, I can go and get some drink. My coffee break. All right. See you.
Okay, welcome to the second part of the session on solar magnetic fields, generation and evolution. And the first speaker will be a remote one, Junwei Zhao from Stanford, and he will be talking about updates and studies of the sun's interior meridional circulation and the sun's far-side imaging. So, Junwei, please go ahead.
Hello, can you hear me?
Yes. Just please start whenever you are ready. Hear me?
Hello?
Hello.
Is this
Do you hear me?
Can you hear me?
Yes, it's all set. Go ahead, please.
Oh, okay. All right. First, I would like to apologize for not being able to go there. I missed the meeting. I feel very sorry about that. Hopefully, I can make this presentation. I made a lot of changes so that I can present it remotely. Today, I would like to emphasize just two different parts of my work. I will start with some basics of helioseismology, and then I will update some progress on the solar rotations and the sun's meridional circulation. I will talk about solar cycles and torsional oscillations, meridional circulations, and its temporal evolution, and our new efforts in frequency-independent studies on meridional circulation. And the last part of the work is about the far-side images and how we calibrate the far-side images into magnetic flux. So the sun oscillates. Everybody knows that. If you look at this movie, this is a movie taken by HMI. It looks like the sun oscillates randomly. But as a matter of fact, these oscillations are not random. They are intrinsically connected to each other. So look at this movie. If I take one point at a random location on the solar surface, and I do cross correlations with other locations, we can find that actually there are ripples is pointing away from that location. So these waves are not surface ripples, but the waves are the waves going into the sun's interior and get reflected back from the surface to the surface, carrying important information from the sun's interior. This is how helioseismology works. So what do we say is what we saw from observations are just the solar surface. What happens in the interior is not very clear to us. Here, what I show is a simulation of one perturbation is started at the top and then it all the way propagates through the sun's interior. What we really care about are the signals. Just meeting when the signals meeting the surface are the parts we can analyze. So this one maybe this one shows the wave paths. So the previous one shows how the waves propagate inside the sun. This one shows the wave paths of the sun. When these waves go into the interior and comes back to the solar surface, it carries information of the sun's interior, such as flows and structures. This is how helioseismology works. Now I will switch to talk about the recent results in the sun's interior rotations. What's shown here is results from Rachel Howe and her collaborators published in 2018 in Image Letters. What they did was to use global helioseismology to derive flow, to derive the solar interior flow rotations. They compared rotation rates from cycle 23 to cycle 24. look at this area. This is latitude below about 25 degrees. These low latitude areas. The solar cycle 24 actually speeds up compared with cycle 23. The rotation gets faster in the low latitudes. But if we look at the higher latitudes above 25 degrees latitude, the rotational speed dramatically reduced by nearly 4 nanohertz. This panel, the left panel shows rotations at 0.99 solar radii, and the right panel shows 0.95 solar radii. Basically, it's a similar thing for these different depths. It speeds up at for latitudes lower than 25 degrees and slows down a lot above that. Recently, just a few months ago, Basu and Antia, they published a paper in ABJ, reported a very similar finding. We can see here, this area, this region slows down quite a lot by about 4 nanohertz, and this area, it doesn't change a lot, but it's 1 nanohertz speed up in the low latitude areas. So that means solar cycle 24 is very different from solar cycle 23 in terms of interior rotations. We can imagine that a lot of angular momentum transport happened during the last 10 years. Okay, and the other thing they reported was torsional oscillation. We understand torsional oscillations are surface pattern, not surface, I'm sorry. It's rotational patterns, some faster bands and slow bands, they corresponding to different regions on the solar of the magnetic field. Usually, they have 2 branches of fast bands. One is poleward from roughly 50 degrees towards the pole, the poleward migrating fast bands. And this one, there's a lower band from roughly 40-something degrees migrating towards the equator together with the activity belt. So there are 2 bands. But if we look at the different panels from top to bottom, they represent different depths. And in each panel, the left part corresponds to cycle 23, and the right part corresponds to cycle 24. If we compare these 2 cycles, there are a number of things we can identify. For example, is a poleward branch of the torsional oscillation. The cycle 24, this poleward branch becomes a lot weaker than the previous cycle. It's very obvious. Another thing, let's look at the lower branch, the mid latitudes, about 30 degrees, 40 degrees latitudes for the lower branch. This is cycle 24, but look at the cycle 25. This part is nearly completely missing. That means the mid latitude, for mid latitude of this lower branch, cycle 25 doesn't show much. Okay, let's continue. If we look at the very low latitudes, below 20 degrees, from 20 degrees to 0 to the equator, so say just this small area here, so it's the cycle 25 already started here, although it's in this plot it's just a very small bit, but it's very clear the next cycle already started, but it's clearly weaker than the previous cycle, weaker than cycle 24. These results are from the global helioseismology. Now let me move on to the near surface rotation and Mourinho flow results from the HMI time distance helioseismology. Here I would like to emphasize just some near surface results. It's like from a surface to 20 megameters below the surface. The left panel here shows magnetic field and flux. These panels cover the 10-year period of HMI. HMI turns nearly 10 years old. It's just a few days from its 10th anniversary. So this covers about 10 years. This magnetic field, we can see a flux transport from the lower latitudes towards the polar regions. These are flux transport. This panel, the second panel, shows magnetic flux. These are just total flux from the last 10 years. Now let's just emphasize the torsion oscillation, because this is something we're more interested in. Compared with the global heliosynchronology results I showed in the previous slides, these are local heliosynchronology results from time distance. The one great advantage of local heliosynchronology is that they can show both hemispheres. It's unlike the global heliosynchronology that only shows symmetrized, hemispherically symmetrized results. Now we can see northern hemisphere and the southern hemisphere separately. There are a number of interesting things we can identify in these plots. This covers 10 years of torsion oscillations. Let's look at the mid-latitudes, mid-latitude branch, the equatorward migrating branch. If we look at this area, the southern hemisphere, comparing southern hemisphere with northern hemisphere, the southern one it started a lot earlier and a lot stronger than northern hemisphere. I think this is very clear. And another thing is, for the last 2 years, from 2018 to 2020, January for 2020, just last month, we can see this branch becomes a lot stronger than the past few years, and the pattern, the southern hemisphere and the northern hemisphere, they show very different patterns. Not very different, but different in strength. The southern hemisphere, look at this region. I'm not sure if you can see my laser pointer. It's here. This flow pattern is very different from the northern hemisphere. The southern one is stronger and more robust than the northern hemisphere. This is what we can see from torsion oscillation. This may indicate that for the cycle 25, right, this corresponds to cycle 25. This is just a starting phase of cycle 25. So if what we observe, what we got here could give us some indication to the activity of the next cycle, I think the southern hemisphere of the next cycle will be a lot stronger than the northern hemisphere, just like the cycle 24. Now let's move on to look at the residual Mourinho circulation. What is residual Mourinho circulation? It is the flow profile, the Mourinho flow profile for each time period. We subtract the 10-year average. So what is left from this subtraction, we call it residual Mourinho flow. In 2004, my colleagues and I reported that residual Mourinho flow, they form a converging pattern on either side of activity belts. So these white contours showed activity belts. So we can see that the activity belts reside in just between a blue band and a red band. The red band is actually poleward flow, and the blue band is equatorward flow. So for this new HMI results, they agree pretty well with my 2004 results based on MDI for cycle 23. Okay, the other fact is we can still talk about hemispheric symmetry. Clear symmetry in southern and northern hemispheres can be seen here. For example, this in the southern hemisphere, this red band is about 2 years longer than the red band in the northern hemisphere. And if you look at this blue region, the blue region in the southern hemisphere is a lot bigger and stronger than the one in the northern hemisphere. If we continue to look at the last 2 years, 2018, 2019, look at this region, these are the red band corresponding to cycle 25. They already appeared, and they already appeared strongly. So this indicates cycle 25 will occur. It's unlike someone predicted that, okay, there was no cycle 25. We're sure cycle 25 is coming. What's shown here are 2 panels, one panel from Northern Hemisphere and one panel from the Southern Hemisphere. There are 2 curves in each panel. The red curve corresponds to magnetic field strength, and the blue curve corresponds to the Mourinho flow velocity. These curves are taken from the 35-degree latitudes. This is from 35-degree Northern Hemisphere. This is from 35-degree Southern Hemisphere. So let's pay attention to the shaded period from 2010 to roughly 2017. If we look at this area, this shaded region, we can find that this red curve and this dark curve, they have very clear anti-correlation. It's very amazing. They have clear anti-correlation. What does it mean? It means that if the magnetic flux is transported toward to strengthen the old field, which is a previous cycle field, the flow speed is faster. But if the flux is transported toward to weaken the old field, the flow speed is slower. It looks like the sun knows what the polarity they are carrying towards the pole. If it's the same polarity as the pole, it's getting faster. If it's a different polarity, different from the pole, then it's slower. It's very interesting. However, this pattern, this anti-correlation pattern, it disappears after the polarity reversal is done, is finished. So this is very interesting, and we don't know much. Why this is the case, and what it implies for the flux transport model of Dynamo model. So I finished talking about the surface patterns, the near surface results of Mourinho circulation. Now let me move on for the deep Mourinho circulation. So ever since 2013, we published a paper on the deep Mourinho circulation. There were a number of publications since then. So all these panels are from different authors, but I got the data and plot them in the same formats and the same color scales, so that they can be directly comparable. This first one was from myself in 2013. It shows the first 2 years of HMI results, and it shows 3 different layers. The second panel shows results from Jason Jakovich. They used GAN data of a few years. And third panel shows results from Rajguru and Angia. I'm pretty sure Rajguru was going to talk about this after my talk. The fourth panel was done by Riju Chen and myself. In this work, we use a different method, different from the other 4 papers. This fifth panel was by Jiaxian Lin and Dingyi Chou. They published these results using MDI observations. So compared all these results, it looks very discouraging, because all these results basically do not agree with each other, not just in structure, not just in magnitude of flows, but also in the basic structures. So it's very annoying. However, if we look very carefully, there's something encouraging. Just the low latitudes, below 15 degrees, roughly below 15 degrees latitudes, we can see that despite discrepancies among different results, there are small but very important agreement. So all these 5 sets of results they showed at least three flow layers in the latitudes below 15 degrees. I think this is very remarkable. Although we have a long way to go to make all these results agree with each other, but so far we have some success in only 15 degrees latitude band. The Mourinho circulation doesn't stay stationary. It also changes with time. This is not surprising. We already saw that in the near surface, but also in the deep interior, it also changes with time. So here we show our results from 2010 to 2018. We showed 4 different representative panels. The first one is the first 2 years. The second panel shows when the northern hemisphere reaches its maximum, and the third panel shows when the southern hemisphere reaches its maximum. And the last one is when the sun became quiet again. If we symmetrize each of these panels, we can make a better comparison. So these 4 panels are just the hemispherically symmetrized results of the previous slide. Look at the first panel. We can see it's clear, this from the first 2 years when the sun was still not active. That's 2010 and 2012. We show clear three flow layers. This may indicate a double cell circulation. However, when the sun became more and more active between 2012 and 2014, we can see that the third layer, the bottom layer, became a lot weaker, and the flow structure is more like a single cell flow structure. But when the sun became less active and entered another minimum, it looks like there are 4 layers, 4 flow layers. So certainly we have to emphasize that we don't know how much these results are impacted by the surface magnetic field. This is always a question that puzzles us. We don't know how to assess if these results are impacted by magnetic field or not. Okay, this is a different way of looking at these results, the temporal variation from Mourinho circulation. So in this slide, we just make a cut across about 15 degree latitudes, 15 degree latitude, and then we plot the depth as a function of time. So this is another hemisphere. We can see that basically most of the time we see 3 layers, but sometimes, for example, this period when it is northern hemisphere is very active, it shows just 2 layers, but near the end of last cycle, it appears there are 4 layers, and the bottom layer, it seems migrates upward, and same thing is the same thing in the southern hemisphere. It's south 15 degrees, and if we look at the higher latitudes at 30 degrees latitudes, they show similar patterns. These are very interesting, but once again, we have to emphasize that we don't know how the magnetic field changes our analysis. So next, I want to talk a little bit about frequency-dependent analysis. We understand that for time-distance heliosystemology, we often do time fitting. That means for one certain travel distance, we're going to have one fitting of travel time, just one number. But actually, this has rich information than just one number. What we do is we just select the first bounds from the time distance diagram, and then we convert it. We do a Fourier transform and make the analysis in the Fourier domain. It has the third panel shows the Fourier domain information. I don't want to go to the details of this analysis because a lot of details that no one else really cares about. Let me just go directly to the results. Here we compare our frequency-dependent analysis with the previous travel time of fitting. The dark curves here showing the previous travel time fittings, and the color curves show the 3.5 megahertz phase shifts. So basically, they are more or less have similar patterns. This is 3.5 megahertz. Now look at the 4.5 megahertz. This is very jumpy. You know, the results is not very consistent with the previous fittings. And this is a 5.5 megahertz. It becomes noisier than the 3.5 and 4.5, but the pattern is still clear. Let's look at this red curve. The speed with the increase of distance, that means the depth. With the increase of depth, the travel time decreases first and then become increase. That indicates multiple flow layers exist below the surface. So I want to say that this frequency-dependent analysis on the Sun's Mourinho circulation is still at its very early stage, and the results look very noisy. However, these results nevertheless indicate multiple layer flow structures inside the Sun. So we will continue to work on this, and hopefully we can make noises lower, and we can do some inversions so that we can compare with our previous results using just travel times. Okay, so for the last few minutes, I would like to introduce the calibration of far-side acoustic images. So in the last few years, I spent a great deal of efforts to develop a new time-distance seismology analysis code to make the science far-side to map the science far-side active regions. So if you look at this movie, the left side is near surface magnetic field observed by HMI. It has positive polarity and negative polarity. And the right-hand side, it shows the images of the far side, acoustic images from the far side. We're able to see the active regions, but we don't know how large, how strong the magnetic field is there. And we simply don't know the polarities of these active regions. So we develop a method by use of deep learning to calibrate our acoustic images into a magnetic field. So basically, the step is we have 3 different steps to do this. First of all, we use AIA's 304 angstrom observations and near surface magnetic field. We do the machine learning training to find a relation between 304 UV images with magnetic field. Then we apply this code on stereo images, because stereo can observe the science far side UV images. We apply the train code on this, and we are able to get far side magnetic flux proxy. This is just a proxy. We don't know how exactly they are. And then we couple the far side magnetic flux proxy together with our acoustic images of the far side. Then we train another deep learning code to calibrate the acoustic images into far side magnetic flux. So we have 3 different steps. Let me show you the 3 steps one by one. The first one is we have AIA UV image. We have HMI image. We have nearly 10 years of these observations, and train the code. Then we can convert one AIA UV image into the magnetic flux image. This is the middle one, and we can compare with HMI observed images. Not the image, I'm sorry, it's magnetic flux. So these are magnetic maps of magnetic flux. So they are very comparable. We have very high confidence that our deep learning code works pretty good. Then the next thing is to apply this code, this deep learning code onto stereo images. Stereo actually they have two satellite spacecraft. One is stereo A, one is stereo B. We apply our code on them separately. So we have magnetic flux maps for a selected period of about 4 years. Here is from 2010 to sometime of 2014. This is a total of 4 years. We have 4 years of far-side magnetic flux maps. Then what we do is, okay, we get we use HMI near side Doppler observations to derive far-side acoustic images. Then we couple. This is one thing, we have acoustic images. The other thing is we combine stereo A and stereo B magnetic flux maps and make a total far-side magnetic flux map. Now we have far-side acoustic maps, we have far-side magnetic flux maps. Then we go to step 3, we train another deep learning code to find a relation between our acoustic images with magnetic flux. So this is one example we want to show how our results look like. This is a far-side acoustic image. This is a stereo far-side magnetic flux map. And this one, the third panel, the last one, which looks very smooth, is magnetic flux calculated from acoustic far-side images. So there are a lot of steps in between. I hope you can understand what we did. There's certainly a lot of work here, but it's very encouraging that we are able to use near-side Doppler observations to get the far-side magnetic flux maps. For this example, for this typical random example, the correlation coefficient is 0.85 between a stereo magnetic flux and our acoustic magnetic flux. This is very encouraging. So in the near future, our plan is to do this in real time. We are able to provide real-time far-side magnetic flux maps. Okay, so here is a summary of what I presented. So there are a few takeaway message. Cycle 24 rotates faster than cycle 23 in low latitude regions, but substantially slower in high latitude regions. Torsional oscillation corresponding to cycle 25 already appeared. For the science deeper Mourinho segregation, there's no consensus. But however, the same result from all different groups indicate that there is a multiple layer flow structure in low latitude regions. Mourinho segregation varies a lot with solar cycle phases. And through deep learning, we are able to calibrate our far-side acoustic images into far-side magnetic flux maps. Okay, thank you very much for your attention. Oh, yes.
Okay, now we try to take questions from you from the audience.
Uh-huh.
Junwai, can you hear me?
Yes.
Okay, so this is Arnav. So I have a question about this your observations of surface meridional circulation, that there is a converging flow near the active regions. And now we know that equation of continuity has to be satisfied. So when you study subsurface flows, do you see any downward flow in the active regions, or what happens to the converging flow? Or in general, when you study meridional circulation, do you also check whether divergence rho v 0 condition is satisfied? And if it is not, then how much it is violated?
I cannot fully understand your question. How about this? Can you send me an email after this? I'm sorry, I cannot hear everything.
Question. So I think Anna wanted to know about the whether the flow satisfies the conservation, whether continuity equation, mass conservation equation.
Yeah.
Oh, right, right. Some of for the some of the authors, they have some of the authors, they already applied the mass conservation equation in their inversions, but some others they don't. So you can tell that, for example, this one, so Rajguru's results and the Riju Chen and my results. For these two results, we already built in a mass conservation equation, so they can fit. They can meet that requirement.
Junwei, this is Dibyendu. Can you hear me?
Can you hear?
Junwei, this is...
No, I didn't.
Okay, I think we'll just drop the question because it's not going to work out.
Can you hear me, Junwei, now?
Yes, yes.
Okay, so I want to kind of make a comment about this comparison that is often made in the heliospheric community with the near-surface flow variations. The transport cycle which is observed at surface layers, right? If you look at the theory of this, work by Hans Kuit and Arthur Semple, for example, thought that the surface variations in the meridional flow and also the torsional oscillations are manifestations of a non-local effect because of magnetic fields in the interior of the sun, and therefore it is expected that that the flow variations will show up before the magnetic flux variations show up in the solar surface, right?
That's right.
I guess you're aware of work from our group by Lexco, who have gone beyond these pretty pictures and tried to make quantitative comparisons between the flow variations and the flux variations, and finds a time delayed effect where the flow variations precede the flux variations. So do you think the community is sort of aware of this and trying to make these connections with this sort of delays and non-local impacts in mind, so that you can come up with more realistic estimates of the cycle continuation?
I didn't get your last part.
What I was asking is whether you guys are aware of this work and this theory behind this near-surface variations, but you can actually incorporate this in your interpretations of what the flow variations will be doing for the solar cycle. I think it's important to consider this.
Okay, I got you. Thanks.
Okay, so we are running out of time, so let's thank our speaker again.
Thank you.
Thank you very much for joining us remotely. Our next speaker is Paul Rajaguru, and he will be talking about the reliability of the measurements of the deep meridional flow.
Okay, can you hear me? Sure, okay. Okay, thanks to Junwei for covering quite a detailed account of how we measure meridional circulation. I will talk about some stuff which we need to worry about, which Junwei touched upon. But anyway, Junwei is still hearing. If you want to go to sleep, you can continue listening to my talk. So there are, sorry. Let me acknowledge contributions from these people here. Professor Antia and the team at TIFR, and also credits to Junwei and Ruizu, and also the team at MPS in Göttingen. So let me again start with just saying the Sun is a very complex fluid dynamic system. What we see here is just cartoons of how the Sun's large-scale motions look like. We have a differential rotation, and the rotation speed is about 2 kilometers per second, which is very large compared to the meridional circulation, which is only 15 meters per second. And the theoretical picture of meridional circulation, which is mostly used in the so-called flux transport dynamo model, looks like this, in a single cell profile. So all of this rotation, convection, there's also large-scale convection in the outer 30%. Theoretical ideas tell you that all these are connected. There are Reynolds stresses due to convection, and the differential rotation drives this kind of flow, meridional flow. And these are really a complex fluid dynamic system. So on the other hand, this is a picture, this is a movie, HMI Doppler observation played as a movie. This again, Junwei showed you. This is what we use to detect these flows in the deep interior. We assume there are, as Junwei mentioned, there are very nice, clear oscillation pattern which is composed of very discrete frequencies of oscillations trapped inside the Sun, and this is a power spectrum. I will not spend much time on this, except to point out that the way we measure these oscillations are due to a spacecraft which is moving at 2 or 3 kilometers per second orbit. There's a large velocity from the motion of the spacecraft, and also when you want to analyze these oscillations to infer what is really happening inside, you need to worry about a lot of other things, like whether the north-south axis of the Sun is aligned before you analyze the data. And those are all going into this pipeline, the so-called pipeline of the helioseismology. There are certain things which you need to worry about, which we don't fully understand. How the 24-hour periodicity of the spacecraft, how that leaks into the Doppler measurements which you make, and how that affects our measurements. I will not be showing some results on that, but I have only 15 minutes. But I just wanted to point out that there are a lot of things which we need to worry about, which we don't fully understand. Okay, so again, this is a simple picture which shows how we measure time-distance helioseismology, meridional flow from time-distance helioseismology. We typically align our measurement arcs in the north-south direction. This is the ray path which corresponds to this surface arcs. If you cross-correlate different distances, which will correspond to getting information from different depths. And that is the basic measurement which we use to infer the meridional flow. Again, let me jump to the results which Junwei already talked about, but I have not been very patient for, like Junwei, to get the data from all these papers and plot in the same color scale, but the color scales are all different here. In my result, the blue corresponds to the southward flow. That means if it is negative, that means it's actually northward. And the color scales are different in this. So just wanted to point out, since Junwei already discussed this, there are disagreements on the measurements. And these are further measurements from a few other authors. And by the way, so the group is very small. The number of people who are doing helioseismology is really, really small. That is one of the reasons we make very slow progress in this field. So this is a kind of an appeal for younger people to jump into helioseismology and address these problems. Okay, so this is the latest result from Mandal Krishnan from TIFR. They use the so-called bond kernels. All the results which are here shown are from the ray kernels. We approximate the ray path, the oscillation path as rays, and do the inversions. Here they managed to derive the bond kernels, the first approximation wave kernels, for using in the inversions of the travel times which we measure. And this is from the travel times which I measured over using about 7 years of data, HMI data from 2010 to 18. We again get very similar to what we earlier published. But as Junwei pointed out, there is a kind of a signature of a double cell at the low latitude. And I will come to this point, Arnab's question about whether that this is actually probably coming from the inflow towards active regions of the flow. This is the radial component of the meridional flow. We use the mass conservation, so we get the radial component or the downward flow also. But it's here, it's not very clear. I'll show in the next picture, which answers your question. So as Junwei did not mention much about the differences in the method of inversion, what we use is we use the stream function, which is got from the continuity equation, which we solve for the stream function, so it automatically takes care of the mass conservation. So we can derive both the components of the meridional flow. Okay, so this is a closer comparison of the inversions with mass conservation and with those without. The obvious difference you can see is there are largest, much fine scale structure, and the magnitude also does not decrease as a function of depth. You would expect that the density increases so steeply inside the sun, you will expect that the meridional flow amplitude might decrease, but that's not the case in these inversions where they do not use mass conservation. When we impose mass conservation while doing the inversion, you get overall a decrease in the magnitude of the flow. And this is what is probably this answers Arnab's question about how the inflow towards active region, whether it causes a downflow. It indeed seems to cause a downflow at the lower latitude. Okay, anyway. So, okay, the main point of my talk, again, these are the cross section of those profiles which I showed. Our conclusion was that there are, if you take a cross section across over depth, is that we seem to get a consistent reversal of the flow around about this depth, about 0.77. So that was our conclusion, that is mostly a single cell meridional flow. Now the main question is that how reliable are these inferences? So there can be two possible approach to address this, whether the travel times you measure are the cause of these differences, or the inversions in the modeling which you do, the input physics and the methods which you use causes this. So I'll try to answer this in the rest of my talk. Let me first introduce, Junwei did not mention the so-called systematics. This is just a quick description of what the systematics are. When you measure the travel times in the north-south direction, this is what you get. And what is shown here is from those you get from the Doppler velocities and the continuum intensities of the data. And if you measure the east-west direction, the arc which is aligned in the east and west, you get a signal like this. So this will correspond to, so by the way, these are measurements after removing the contribution of rotation. So there is no rotation signal here. So what would that mean is that since there's a change of sign near the central meridian, you would see that it will correspond to a flow from the central meridian to on the both hemispheres in the opposite side, which is not real, which is not physical. So this is, we assume that this is systematics. And in a few papers, a series of papers, Junwei showed that this is indeed systematics. So what we do is we rotate this in 90 degree and subtract it from the north-south measurements, because these north-south measurements also should be having the systematics. So we remove that. So that is how it is done. I will skip this slide. These work by Junwei shows that those are indeed systematics. Okay. Now, what we have been doing, I mean, after all these differing results were published, we formed a team in EC in Bern to really closely look at what's really going on. One of the things we figured out to do is Junwei also touched on this, to frequency filter the oscillation which you use for measuring travel times, and then do it at different frequencies. So that's what we did. These are 1 millihertz width bands in frequency, centered at these frequencies, and filter the oscillations, and then do the measurements. So what we found is these are the signals and the systematics, the systematic which I just showed you. So there is a very strong frequency dependence in the systematics, which you see. So at about 4 millihertz, you see at a very large value. You can see the scale here. This goes from -5 to +5 seconds, whereas the signals are of the order of 1 second. So there are the systematic is about 5 times the signal which you want to measure. So there is a very large systematics, and there is a very strong frequency dependence. So by the way, the systematics which we subtract, we don't understand where it is coming from. The method which Junwei showed and which established that it's a systematics is just an ad hoc method. So we don't understand where it is coming from. But on top of that, this has these properties, which are a very strong frequency dependence. So what we did was that you measure the systematics at these frequencies, and we get the signals at those different frequencies. As you can obviously see, what is plotted here is the latitude versus the travel distance. The travel distance corresponds to the depth inside the sun. So as you can see, there is a very strong differences in the travel times at different frequencies. As you go to higher frequencies, you see the color changing, the travel times, which I will show you the inversions in the next slide. Okay, before I go to that, if I plot this as a function of frequency and depth or the travel distance, the problem is that the larger the distance or the deeper you go, the larger is the systematics, which you see here. And the signals, you see some kind of a correspondence between the larger the systematics, the more blue in your signal here. That means your real travel times seem to be influenced by this structure here. Because you have a kind of a correlating structure in the signals and the systematics. So this would indicate that if you are making an error in estimating the systematics, that will cause errors in your signals. And that is indeed what is happening. And this is what we do. We did the inversions for these different frequencies. What you can see here is that to lower frequencies, where the systematics is low, and you seem to get a single cell structure. But as you go to higher frequencies, you get a double cell, very clear double cell structure. So, so the conclusion is that maybe we are not dealing with the systematics correctly, since it can give such a, but the real sun cannot be like this, right? Your sun can be have just one flow structure. So you cannot, the sun cannot be showing a different phase at different frequencies. So that means that obviously we are not correct. We are not doing it correctly. So that is a main conclusion, and I will let me show you this. So if you do the joint inversions of all the individual frequencies travel times, and you do get a double cell structure. But on the other hand, if you do the unfiltered travel times, you get a single cell structure. So that it again points to the fact that we are not doing it correctly. So the summary so far, I have some more slides. How much time I have? 2 minutes. Oh, okay. So this is the summary so far, and I wanted to show you these temporal variations. Probably I will skip this. Junwei talked about it. I wanted to show you this frequency dependence on the near surface variation. These are the fluctuations in meridional flow, which you measure. After subtracting the mean meridional flow over time, x-axis is the time, and this is the magnetic flux, which Junwei also showed. The point I wanted to make was that this is at 3 millihertz and this is at 4.5 millihertz, where we saw very different deeper structure. But for the near surface flows, there isn't much difference in the pattern of the flows. These are what Junwei talked about, the inflows towards the active regions. This is the flow towards the active region. This again, the blue is coming from the higher latitude towards the active region. This is from the lower latitude towards the active region. So that structure is seen in all the different frequencies, although the structure, there is slightly a higher frequency spatial structure in the higher frequency measurements. But what I wanted to stress is that at the near surface layer, there is a general agreement for this temporal variation of meridional flow. So that means that again, it indicates that when we try to deal with deeper layers where the systematics is very large, we are making an error. So that is my main conclusion. And there are a lot of other things, other dirty things like what I mentioned during the beginning of my talk. There is a group in MPS, I just showed you in the first slide. The results are not yet published. They show very strange dependence of spacecraft velocity. Within a day, the spacecraft goes from -3 kilometers per second to +3 kilometers per second. If you use oscillations measured only during the zero crossing of the spacecraft, okay, those show very different meridional flow structure than what you use if you use the full data. So it's really dirty stuff here. I mean, but then since what is at stake is the very profound internal dynamics of the sun, which we need to worry about. So we need more people to figure out what is really going on, and probably I'll stop here.
Thank you very much for this very interesting talk. So questions, couple of quick questions we could take. Yeah. Okay, Anna.
So you asked more young people to join this field, but with more people, how will these controversies be resolved? Will there be new data coming, or generally do you think in the next few years it will continue like this, or there will be a convergence among helioseismology results?
No, the point is there are a lot of things to address. These are really very diverse topics within this helioseismology. You need to worry about how the oscillations are measured, first of all. You need someone who understands the instrumentation as well as the data processing and all that. And then this systematics, which we don't know where it is coming from. We need someone who is an expert in radiative transfer, how the waves, helioseismic oscillations behave in the atmospheric layers. We need people who are experts in those details. Need to focus on this, because generally traditional helioseismology, as we are trained, we are not dealing with those things. So that probably is one aspect of what answer to your question. But yeah, I mean, it's not that the more people work, they will completely. I mean, it will completely solve the problem. But yeah, but that can help.
Okay, one more quick question.
Yeah. So I mean, if you measure if you have a good result in the near the surface and at least in the upper convection zone, and if you impose this mass conservation condition, then actually then the rest of the then the lower convection zone, the flow in the lower convection is automatically will have equatorial flow. Yeah. So I'm just wondering, like, how does this mass conservation is actually going to affect the actual signal?
No. As I showed you, the mass conservation is not the difference in the different solution which I get, which is the main point of my talk was to show that how you remove the systematics. So there is a very strong frequency dependence. At different frequency, there are different amount of systematics. That is what leading to the different results in the deeper layers. So despite the mass conservation, we are using mass conservation in all these inversions, which I showed you.
Okay.
Okay, let's thank the speaker again and move on. So our next speaker will be Lakshmi, talking about solar cycle variation of large-scale plasma flows.
Good afternoon. I'm talking, actually the title of my talk is slightly changed. I will be talking on the solar cycle variation of meridional flow. So the background of this slide is the meridional flow velocities, the time varying component of the meridional flow velocities obtained from Gong ring diagram pipeline. So let me start my talk with a motivation, and it lies in the solar dynamo mechanism. We know the initial poloidal field is stretched by the differential rotation to generate the toroidal field, and the conversion of toroidal field to poloidal field can be explained either by mean field alpha effect or by BL mechanism, where in the mean field alpha effect the turbulent convection plays a vital role, and in the BL mechanism the tilted sunspot groups on diffusion, the flux from these tilted sunspot groups are transported towards the poles by the meridional flow. As Vidya had mentioned already in his talk, that the tilt plays a very important role in this mechanism. Now, if you look at the cycle amplitude and polar flux over past 100 years, you can see that the polar flux is not really linearly correlated with the cycle amplitude. Say for cycle 19, if you see, the cycle amplitude is quite large compared to the other cycles, where the corresponding flux, polar flux, is comparable or like less than the other cycles. That means there is some quenching mechanism that's happening in the conversion of this toroidal to the poloidal field. According to the mean field dynamo, if the strong flux tubes rising through the convection zone, then the helical turbulent convection becomes ineffective. And according to the BL mechanism, this quenching can be explained through two processes. One is the before emergence, before the active region emergence. If the flux tubes are strong enough, then the tilt, then it gets less time to be acted upon by the Coriolis force, and the tilt will be reduced. Now, after emergence, there can be reduction in the tilt because of the surface flow effects. So let me explain something in detail about the surface flow effects. It's observed through helioseismology and feature tracking methods that the horizontal velocities have components converging towards the active latitude or towards the regions of strong magnetic field. Now, it's believed that the inflow of this plasma towards the active regions can provide critical nonlinear feedback to the solar cycle. So this is the image of one active region. The field is plotted as contour, and the arrows represents the horizontal velocities, the horizontal and meridional flow velocity components. So the arrow heads points towards the direction of the flow, and the length of the arrow represents the flow velocity strength. Here we can see that wherever there is strong magnetic field, there is a converging flow towards those regions. Now, we will be looking at this inflow of plasma towards the active regions. For that, we will be using the meridional flow velocities obtained from the Gong ring diagram pipeline and the magnetic flux obtained from MDI or HMI. Also, we calculate the residual velocity, which is a time varying component of meridional flow velocity, by subtracting out the mean velocities over a period of 11 years at each latitude. So the residual velocity which we get represents the variation due to the various magnetic forces, where we have removed out the perturbations due to other effects. So in this plot, the contours represents the magnetic flux over the period, over our observing period from 2002 to 2018. And the arrows represents the flow velocities, residual meridional flow velocities. So the arrowheads points towards the direction of the flow, and the length of the arrow represents the strength of the flow. Here you can see that there are converging flows towards the active latitude belt. So we quantify, in order to study the effect of these flows on the tilt angles, we need to quantify the inflows. For that, we calculate the active latitude of the centroid for each solar rotation by this relation, and the latitude, the active latitude is fitted by a straight line, and the 99% by dividing this into two separate cycles, cycle 23 and 24 for each hemisphere, and the 99% confidence bound gives us the active latitude band. Now we define the convergence or divergence, that's the inflow or outflow of plasma, by this relation, where the positive value of net velocity represents the divergence or the outflow, and negative value represents the convergence or the inflow. Sorry. Also, we calculate the net magnetic flux, which is the sum of the flux over the active latitude band which we have defined. Now, if we plot the net flow as a function of magnetic flux, we can see that for the low values of net magnetic flux, the net flow is mainly positive, and for larger values it's negative. That means that if there is a stronger magnetic flux, the flow converges towards the active latitude, or it becomes negative. That means there is an inflow of plasma towards the active latitude. Now we need to study how the inflow or outflow of plasma affects the tilt angle. For that, we see that tilt angle show deviation from the Joyce-Low tilt over the solar cycle. And considering the force balance equation, we can derive an expression connecting the emergence tilt, initial magnetic field, and the total flux of the loop. So we derive an expression using this force balance equations and for the theoretical tilt value, which is expected. Now we calculate the tilt scatter, which is the difference of the observed tilt from the theoretical tilt. So if we plot the bint scatter, tilt scatter as a function of net flow, we see that there is a significant correlation between the two. That means if the net flow is negative, that means if there is an inflow, the tilt scatter is negative. That means there is a reduction in the tilt value, expected tilt value. And if the net flow is positive, that means that expected tilt value increases. So we need to study how this inflow, the reduction in tilt, is going to modify the poloidal field evolution. For that, we define the factor, the product of alpha tilt and the active region flux as the empirical source term for the BL mechanism. If we plot this one as a function of, plot the source as a function of active latitude flux, we see this, that for large values of flux, we see that it deviates from a linear relationship. This can be seen better if we bin the values. Here we can see that beyond like 1.4 and 10 power 23 Maxwell, we can see that there is a deviation from the linear relationship and kind of saturates after this. And the Spearman correlation is 0.93 here, which means that this clearly we can see the nonlinear quenching that's happening in the BL dynamo as expected. So our conclusion is, we find that the inflow or outflow of plasma towards the active region is strongly correlated with the magnetic flux. We observe that the converging plasma flows will reduce the active region tilt angle. Also, this is the first direct evidence of the hypothesized quenching of BL poloidal field mechanism driven by the plasma inflows into the areas of strong magnetic field. Thank you.
Thank you very much. Questions for Lakshmi? Vidya?
Yeah. So, I mean, I could not completely understand the plot, just, this one.
Okay.
So you're showing, can you just tell me this plot once again?
So here, the y-axis is a source term, which is defined as a product of the tilt, observed tilt, and the active latitude flux. It's plotted as a function of the active latitude flux. Here you can see that after beyond like 1.4 into 10 power 23 Maxwell, you can see that it's becoming nonlinear. So that's what expected from the BL dynamo.
Okay.
Like nonlinear quenching which you expect.
Yeah. Yeah, another comment, like when you're comparing with this theory of this, thin flux tube. So one thing we should remember that they are the magnetic field B0 and the flux, they are actually the flux and magnetic field strength of the initial flux, okay, initial flux tube, but not on the surface.
Yes, yes. I understand. So that one I have used the values which is observed from theory. It's expected from the theory.
So in regard to the inflow towards active regions, if I remember correctly, there's a paper by Hank Sprout quite some time back, which uses the thermal driving of inflow, not really due to magnetic flux acting on the flow.
So it, what I understand is like when there is a stronger, when there is an active region, there is a temperature gradient, which leads to a pressure gradient. Finally, so the balance between the pressure gradient and the Coriolis force can create a geostrophic flow, which can be. So it was kind of explanation which was given in Sprout's paper.
Right. Now what I'm pointing at is that you can derive a relation between magnetic field strength and the temperature difference, for example.
Yes.
If you put in that here in terms of temperature, I'm wondering if you will get a, I mean, this power law which goes as B minus 5 to 4, whether that will kind of agree with what Hank Sprout theory, which
so that temperature gradient is coming from the magnetic flux itself, right?
Okay.
Because like stronger active regions means the temperature will be less. There will be a temperature gradient in those regions.
Okay. Well, actually, I had one question.
Yes.
In your model, do you have only the Babcock-Leeton alpha, or do you also have the so-called mean field alpha
No,
effect?
here I have considered only the BL.
Okay. Okay, let's thank Lakshmi again.
Thank you.
And then we go to the last talk of this session by Prantika Povmik about the prediction of the sunspot cycle 25.
So good afternoon everybody, I am Prantika. I am working right now as a postdoctoral fellow in Durham University with Anthony Yates. But this particular work that, okay, so it's not coming. So this particular work that I am going to present today was done during my PhD at CSC when I was working with Professor Dibyendu Nandi. So Dibyendu has already given a great overview on why we need to predict sunspot cycles. So we know that solar variation modulates the radiative, electromagnetic and particulate environment in the heliosphere, creating weather in space, and much of the solar activity is magnetic in nature and closely associated with sunspots. So the number of sunspots appearing on the solar surface varies over time with a rough periodicity of 11 years, but the amplitude of the sunspot varies from cycle to cycle and without any apparent similarities. So right now we are at the minimum of solar cycle 24, and this study predicts how the solar cycle 25 is going to look like. So Dibyendu has already talked about the basic physical mechanism that governs the magnetic activity of the sun. Still I will say, like, we know that dynamo mechanism that works within the solar convection zone actually governs the variation in solar magnetic activity. Within the dynamo mechanism, the two components of magnetic field, so the toroidal and poloidal component interchange between themselves with a rough periodicity of 11 years, where the generation of toroidal to poloidal component happens through Babcock-Leeton mechanism, and the generation from poloidal to toroidal component happens through omega effect due to the differential rotation. So I will be briefly talking about how the Babcock-Leeton mechanism works. So sunspots on the solar surface appears as bipolar magnetic region with opposite magnetic polarities, such that in presence of large scale velocity fields such as meridional circulation and differential rotation as well as turbulent diffusion, flux from the leading polarities cancel between each other due to cross secretarial cancellation, and flux from the following polarities goes towards the pole and alters the existing like dipolar magnetic field. So the models that studies the evolution on the solar surface are known as surface flux transport model. So for this particular study, we developed one data driven surface flux transport model at CESI. So in this model, we solve the magnetic induction equation, and we solve only the radial component of the induction equation on the solar surface, where Br is the radial component of magnetic field. This omega theta is the differential rotation observed on the solar surface. V theta corresponds to the meridional circulation and eta corresponds to the diffusivity. This S term particularly shows how the corresponds to the emergence of new sunspots during the solar cycle. So the numerical model that we have used to develop this model is based on spherical harmonics technique. So moving on to the transport parameters that we have used is one of the large scale velocity field, that is meridional circulation. We have used an empirical profile where the it's an axisymmetric profile where the peak speed is 15 meter per second and the peak happens near mid latitudes. For diffusion coefficient, we have used a constant value of 250 kilometers square per second. And finally, for the differential rotation profile, we have used an empirical profile where the equator rotates faster than the polar region. With all these parameters, so as I was telling, like the model that we have used is a data driven model. So the source of data is coming from Royal Observatory Greenwich and USAF NOAA database. So they provide information about the tilt of emergence, of the time of emergence, latitudinal, longitudinal position of the sunspot, and also the area. So additionally, to model the sunspot, we also need information about the tilt of sunspot, as the previous speakers have told you the importance of tilt in the Backward-Linton mechanism. So we use a modified Joyce law where there is a cycle dependent factor, where if the solar cycle is very strong, then the tilt angle will be the average tilt angle of all the sunspot associated with that cycle will be reduced by a factor. For the flux, that is proportional to the area. So these are like the basic parameters and particulars about the model. So with this setup, we performed a century scale calibrated data driven simulation over the period of 1913 to 2016, and it covers solar cycles 15 to 24. So once our model is ready, the next part is how we validate the simulation generated results with the observation. So what are the observed manifestation of the Backward-Linton mechanism? So as we know, the Backward-Linton mechanism produces the polar flux. So this particular this particular plot taken from observational studies shows that polar flux during cycle minimum reaches its maximum amplitude, and during cycle maximum it reverses its sign in both hemispheres. So I just want to remind you the time variation in the toroidal field is captured in the sunspot cycles, and the evolution of the poloidal field component of the magnetic field is captured in the polar flux evolution. So moving on to the validation of our model. So this particular figure shows the total Einstein flux associated with the sunspot that used as input in our SFT model for the cycle starting from cycle 15 to cycle 24. So that observational data that we have used was available till October 2016 here. It was almost like in the descending phase of solar cycle 24. So using this data, we have calculated what the SFT model is giving as the polar flux. So polar flux is the magnetic flux that is there in the polar curve region that spans from 70 degrees to 90 degrees in both the hemispheres. So in this particular image, the lighter red and blue curve with error bars are the polar flux obtained from observation in the south hemisphere and the northern hemisphere correspondingly. So the darker curve in red and blue showing what the SFT model is generating during this long simulation. So I will be particularly showing the like comparison after this dotted bar, because when we start the simulation, we started with a less constrained initial condition, because the simulation started in 1913 where we didn't have any magnetic field observation on the solar surface. So when we performed a correlation analysis between the polar flux at cycle minimum with between observed and simulated values, we found a quite strong correlation analysis, correlation coefficient of 0.88 with high confidence level. And I want to point out one, so there you can see a discrepancy between the observed and simulated polar flux. This primarily happened during the minimum of cycle 19, and we all know that cycle 19 was like different kind of cycle compared to the other ones, because it was like really strong cycle. So moving on, this gives us quite a confidence, like the SFT model that we are using is working quite well. So the next part is how we can use this SFT model for the prediction purpose of solar cycle 24. So the first question that may arise, like how far we can predict in the future. So as Dibendu was saying, solar cycle has short memory and reliable prediction can be done only half a cycle before. And the polar field during solar minimum can act as like one of the best proxy to predict the next solar cycle. But if we want to use a dynamo model to predict the next sunspot cycle, we have to reach the solar minimum first to use the polar field at that time. When this study was done, we are still like 3 years away from the solar minimum. So actually we developed one methodology where we can extend this time window. That means we do not need to wait for sunspot minimum to occur by first utilizing the surface flux transport model to predict the polar field at cycle minimum first, and subsequently using that to drive a dynamo model to predict the sunspot cycle, predict the next sunspot cycle. So as I was saying, so the observational data that we used for this SFT model was available till cycle 24, till the descending phase of cycle 24 till October 2016. So we first need to model the last 3 years of or 2.5 years of cycle 24 descending phase. So we use synthetic input profiles by varying the tilt angle of the sunspots, also like the flux content and latitudinal position of the sunspots. We used 140 such profiles to predict the polar field during the cycle minimum period. So this dotted line shows till which we had the observational data. Rest of the part is our prediction. So this prediction was done like 2 years back. So now if we compare with the actual observed polar field, like updated polar field, so you can see like in the southern hemisphere what we predicted, this sudden decrease in the polar field is also seen in the observation right now. So our prediction actually captured what is observed now. So this particular plot is showing the predicted surface map, one of the predicted surface map at solar cycle 24 minimum. So the next part is like how we are going to assimilate the SFT generated results in the Dynamo simulation. So what we did, like during every solar minimum, we utilized the surface magnetic field and modified the vector potential of the Dynamo model and drive the century scale Dynamo simulation. So the Dynamo model that we have used in this study is like updated version of Surya, excuse me, updated version of Surya, that is a two-dimensional Dynamo model. And I want to emphasize that during this century scale simulation, none of the profiles or parameters were altered both in the SFT model or in the Dynamo model. So to explain how we assimilated the surface map obtained from SFT model in the Dynamo model. So from the SFT model we have surface magnetic field. From that surface magnetic field we can calculate the corresponding vector potential on the surface, and correspondingly from the simultaneous Dynamo model we can calculate the vector potential on the solar surface. If we take a ratio between these two vector potentials on the solar surface, we will get a latitude dependent factor gamma on the surface. So this gamma preserves the hemispheric asymmetry in the magnetic field according to the solar surface magnetic field. So to explain it in a better way, so suppose this is like the surface magnetic field map at solar minimum. If we do a longitudinal average of this surface magnetic field map, we will get a dipolar magnetic field as expected during solar minimum. So by integrating this surface magnetic field as a function of theta. So we will get a corresponding vector potential on the solar surface, which is given by this orange curve. The corresponding vector potential coming from the Dynamo model is given by this dotted blue curve. If we take a ratio between these two, we will get a profile which is dependent on the surface magnetic field and is a function of latitude only. So how we modified the poloidal field source term in the Dynamo model is that suppose this was the dipolar magnetic profile of the vector potential in the Dynamo model. So we multiplied this gamma factor on the top of it from 0.8 solar radius to the surface and modified the vector potential, that is like assimilation of the SFT map in the Dynamo model. So as you can see, because of the inclusion of the surface magnetic field, it is giving an asymmetric profile. So we did this the similar kind of assimilation at every solar minimum. So and we calculated the solar activity obtained from the Dynamo simulation. So the black curve or in the background is showing what is observed during the last 10 solar cycles, and this magenta curve is showing what we got from the simulation, from Dynamo simulation when we introduced the SFT results in the Dynamo simulation. So then further we did a linear correlation analysis between the peak amplitude of the solar activity obtained from observation and simulation, and we found that it is strongly correlated with 0.87 with a high confidence level. So this gives us the confidence like this assimilation scheme that we are using is working quite well for the past 8 solar cycles. So and that we can use this scheme for the prediction purpose. So as we are saying, like we already had 140 different realization of the solar cycle minimum of the cycle minimum surface magnetic field of cycle 24. We use those 140 profiles to give an ensemble forecast of solar cycle 25. So this is how the solar cycle 25 looks like. So the magenta curve gives like the average of ensemble forecast with the range of this ensemble forecast. Yeah, and so to precisely saying solar cycle 25 is going to be a weak solar cycle. It is going to be similar to solar cycle 24 or maybe slightly longer. To give a precise number, so we predict that the mean sunspot number, like this magenta curve, the yearly mean sunspot number is going to be 118 during solar cycle 25. The time of peak activity is going to be around 2024, and the sunspot number during solar cycle 24 was 113. So you can see like it's almost similar to cycle 24. Again, like because it was an ensemble average, we got a range also. As you can see, the range varies from 109 to 139. So it's like it's going to be an weak cycle. So to conclude, like we have performed the first century scale observational data driven simulation of the solar magnetic field both on the surface as well as in the interior, which successfully reproduced the past 8 solar cycles as well as predicted the next solar cycle 25. Another thing we found during doing this study is like the variation in the solar activity or during the last century can be captured only varying the poloidal field source term that is originated from the BL mechanism. And lastly, like our ensemble forecast suggests that the near Earth space weather is going to be almost similar or marginally extreme in the coming decade as compared to the current solar cycle 24. And there is no indication of sliding of that sun is going to slide into a Mondor minima like phase. So yeah, thank you.
Thank you very much. So we have time for a couple of questions. Okay, Vidya.
Yeah, so putting this data, the magnetic field data, surface magnetic field data, the idea is, I think, is basically same as like this Arnav and other they did. Okay. Yeah. So yeah, first of all, I have one comment is that like so in India we have this Kodaikanal solar from Kodaikanal Solar Observatory, you have this polar active network that gives a very good measure of the polar magnetic field. So I mean, my comment is like, why don't you I mean, use that data instead of like a polar faculae data.
So we have used the polar faculae data for only comparing the SFT generated polar flux.
Yeah, so I'm saying that you can also compare with the polar active network, which is a good proxy of the polar magnetic field. And we have the data also for roughly like 100 years. And yeah, so okay, so my
like for using the surface, using like the Dynamo model, we can't only work with the polar flux. We need like the way we are assimilating the data, we need the whole surface map. Only the polar faculae or the polar flux will not work.
Okay, yeah, so one question is that like, so the flux emergence process is, I mean, is a complicated process and you do not understand. So, and all the prediction model, we use the polar magnetic field and predict the next cycle strength. So do you believe that there's any nonlinearity, if there is, in the flux emergence process, is going to change the strength of the solar cycle?
Yeah, I mean, it can. So the thing is, like, of course, it can change the strength of the solar cycle, but again, like, how much it will change, it will depend. I mean, because like we are doing an ensemble forecast, we believe that the change due to this nonlinearity will be already captured in the range that we are giving.
Okay, one more quick question.
Yeah, if you look at closely this, you're also not able to reproduce the double peak, which is also an element which I think Vidya has pointed out. So in your prediction, which is the peak, will be largely also been a subjective, because if you have a double peak, whether you call it the first one as a maxima or the next one is always an ambiguity. So is it possible in your thing to incorporate these behaviors of sudden fluxes, which is going to the pole, which is of opposite polarity and so on?
So yeah, so the thing is, like, if I see, okay, maybe I can. So if this is like the butterfly diagram obtained from the SFT model, so if you closely see, like we see like the opposite polarities are going towards the polar region. So the SFT model that we are using is being able to capture that scenario. And about the double peak that you were asking about, so the plot that I was showing was like primarily the yearly sunspot number. So when we do an yearly average, sometimes we miss the double peak. So I did another study on like how to capture the hemispheric asymmetry on the sunspot cycle. There I have found, like, yeah, only considering the BL mechanism during like the BL mechanism source term at solar minimum, we can capture like largely about this double peak nature in the solar cycle.
Yeah, because that could be also useful, because if we say 2014 is the max.
Later. Like I have recently published this work in A&A. Okay. I mean, very recently, like last month.
Okay, good.
Okay, I think it's time to wrap up this session. Let's thank the speaker and all the other speakers again.
Thank you.
So there was some request that you wanted to exchange money. So we'll arrange somebody to come tomorrow at 1 o'clock, and you can change your currency into Indian currency. We'll go out, we'll have a conference photo, and then